Welcome to this course, Introduction to MongoDB. This course is part of our specialization, MongoDB Analytics, which has been designed to provide you with a broader understanding of how to fully utilize MongoDB from a data science and analytics perspective. Obviously, we need to start from the beginning and provide you with the knowledge foundation on how MongoDB works, how to operate with MongoDB, and where it fits your development practices before starting a full-fledged MongoDB journey. In this course, you will learn the fundamentals of MongoDB that are needed to fully understand how to leverage its power to perform analytics. These fundamentals will include topics like MongoDB's document model, importing data into a MongoDB cluster, or working with the MongoDB CRUD API, alongside with an introduction to MongoDB's aggregation framework. These topics will be explained to you by the means of a demo application, Mflix, which is a video streaming application similar to popular online streaming services. This will give you a great first encounter of how simple and practical it can be to build applications with MongoDB. In addition to these essential topics, you will also learn and work with useful MongoDB tools and services. Especially, you will work with MongoDB Atlas, our database as a service, MongoDB Compass, our schema visualization tool, as well as many other useful command line utilities. This course is for newcomers to the MongoDB family, so no prior MongoDB expertise is expected. That said, we do have some technical requirements that you should be aware of. We will be expecting you to know about Python, the most beautiful language in the world. This is the language of choice throughout this specialization. We will ask you to have Python 3 environment set up in your workstation. Finally, I just want to welcome you again to this first course on MongoDB. We hope that you enjoy the material we prepared for you, and we wish you the best of luck. And I'll see you in class.
Okay, before we do anything in this course, we need to understand what the MongoDB document model really is. If you're familiar with JSON, JSON makes a great mental model for what records in MongoDB look like. In a relational database, you simply store rows in a table, and each row is a record. MongoDB is a document database, and the type of record that's stored in MongoDB, or a document, is a hierarchical data structure that matches the type of data structure you'll see in high-level programming languages like Python. You can think of MongoDB as storing JSON documents. So if you're familiar with JSON, you'll be very comfortable with what's possible in terms of a structure for documents in MongoDB. A MongoDB document consists of fields. Each field has a key and a value. So here, these are keys, and these are values. Where things get interesting is that values can be integers, they can be strings, they can be floating point numbers, but they can also be arrays, embedded documents or arrays that contain embedded documents. There are essentially three different structures that values in MongoDB can take on. Those are scalar values, such as an integer, a floating point number, or a string. Dates would be another type of scalar value. Then there are arrays. And finally, as values, you can have documents. Here's another example here. The idea here is that MongoDB allows application developers to model their data in a way that makes the most sense for an application. Here we have an example drawn from the e-commerce space. And this data is modeled so that reads and writes to the database are as efficient as possible. As a data scientist, you will both have to work with application data that is stored in a MongoDB database, especially with the increasing popularity of MongoDB. But there are also advantages as a data scientist in storing your data in MongoDB, and those advantages align pretty closely with the reason why developers use MongoDB. You have the ability to interact with the database in a much more efficient manner than you can with a relational database because we can construct complex structures like this, and the MongoDB query language, secondary indexes, and built-in analytics tools such as the MongoDB aggregation framework all support these data models. So here we have an example that represents a particular type of shoe. And what's interesting here is that we're able to represent all of the attributes of the shoe and all of the variants for this shoe. So what we mean by variants here are all of the different choices you can make as a consumer for this shoe. So size, color, and so on. And the way this data model is designed, we can construct an index that would allow us to query for all shoes for which we actually had a size 6 in orange in stock, for example. From the application developer's standpoint, the idea here is that we can store everything we need to store in a single document so that we can render a web page with a single request to the database. So rather than doing joins across multiple tables, which is necessarily less efficient, we do a simple request. All of the data is stored sequentially in the same place on disk and in memory, and the request ends up being very fast. Note that here in this data model, we're actually including the reviews in with the product data itself, again, so that we can do a single request to the database to produce the web page that would be generated by this particular document. As a data scientist, especially as you get more and more comfortable with the MongoDB query language and the aggregation framework, you can leverage this same query efficiency for the different types of analysis that you'll want to do on whatever data set it is you're working with. So again, the takeaways for the MongoDB document model are: think of it as JSON, or think of it as a dictionary in Python. And within that dictionary, values can be scalars, they can be arrays, or they can themselves be dictionaries. And you can have any level of embedding and nesting that makes sense for your particular application. Now, of course, you could have a completely flat data model, if you so desired, with simply keys and values, and all of the values being scalar. But there's usually a good reason to have some level of hierarchy in your data model, and typically that reason is one of efficiency or simplicity in terms of working with the data. One advantage of using MongoDB for data science is that it is trivial to get data into MongoDB and easy to change your data model as needed to support analysis. With our data in MongoDB, we can take advantage of indexes, the MongoDB query language, and the aggregation framework to manipulate and explore data efficiently as we work to better understand and refine our requirements. MongoDB provides a free tier option in Atlas, which is perfect for getting started. Atlas is a MongoDB hosting service provided by the people who build MongoDB. It's easy to migrate data from the free tier to production-scale databases when you're ready. To get started, please sign up for MongoDB Atlas, visiting the link provided in the lecture notes for this lesson. We'll be loading some initial data sets that we will clean up and begin analyzing as soon as we're done creating an Atlas cluster. Please create an account and save your credentials somewhere. Once you've submitted an account creation form, you'll be prompted to create a group. Atlas uses groups to enable you to control who has access to your data. As is often the case, you can grant full read-write access to some users, such as the data scientists on your team, and read-only access to others. Please enter Analytics as the group name. Throughout this course, we'll give you pretty specific instructions on setup tasks such as this, so that if you have trouble, it's easy to diagnose the issue. Once you've created a group, you'll be taken to a screen like this. Please note that as with all websites, Atlas is actively developed. The user interface you see may look a little different from what we see here. Note also that Atlas uses intercom, and you might see a welcome message when you first create an account. Now, don't be nervous about the fact that you see a cost here under pricing. Just select M0 here under instance size, and you'll see the price go to 0. Also, let's name this cluster Mflix. This is the name of the app we'll be building as we move through this course.
Once you've named the cluster and selected M0 as the instance size, please scroll to the bottom of this modal and create an administrative user with the username analytics and the password analytics-password. We'll use these credentials to connect to this MongoDB cluster from Python scripts and applications later in this course. Now, if the term cluster is unfamiliar to you, don't worry. All you need to know at this point is that a cluster provides redundancy. The cluster we are creating is actually 3 MongoDB database servers. This is a safeguard to make sure your data is always available to you. While the probability is small of something going wrong on any given day, computers crash, network connections break, and other problems emerge. Having a cluster rather than just a standalone instance ensures that you'll be able to access your data, even if something bad happens to one of the servers in our cluster. The client libraries we will use from Python will automatically switch to one of the other servers if, for some reason, it can no longer communicate with the one it was reading from and writing to. This is called automatic failover. All nodes in the cluster maintain copies of your data, so it really doesn't matter which one your application uses. All this is handled for you automatically. You probably won't even notice if a failover happens. Okay, with that little bit of context about what a cluster is, click Confirm and Deploy to initiate the creation process. You might see a CAPTCHA pop up. Simply do what it asks you to do. Verify. It will take a minute or two for your clusters to be created. While we wait, let's ensure we can access our cluster once we begin to write a little Python code. Click the Security tab, then click the IP Whitelist tab. Click the Add IP Address button, and then the Allow Access from Anywhere button. And finally, confirm. Atlas allows us to restrict access to a cluster to specific IP address ranges to, for example, ensure only computers in a specific corporate network can connect to the cluster. Allowing access from anywhere will make it easy for you to access MongoDB from wherever you are, and simplifies access for this course. You will still need to supply a username and password to access the cluster. Now click the Clusters tab, and wait for your cluster to finish initializing.
Compass doesn't yet fully support the entire MongoDB query language. So in order to do some of the lessons in this course, we're going to need to use the Mongo shell. The Mongo shell is a text-based client that fully supports all MongoDB CRUD operations. In this lesson, I'm going to walk you through installing the Mongo shell on a Windows machine. Here we have a Windows 10 environment. I'll also show you some of the subtle differences you'll encounter when installing on Windows 7. There aren't many, and you should be fine on Windows 10 or on older versions of Windows, provided they are 64-bit versions of Windows. Now, to install the Mongo shell, we're actually going to install MongoDB itself. We're going to install the enterprise server. The shell comes packaged with the server as part of the download from the MongoDB Download Center. So please navigate to the Download Center, and then instead of Community Server, let's click the Enterprise Server tab, and I will select Windows. Now, this is very important. Even if you already have MongoDB installed, please go through these steps. Earlier versions of MongoDB in the shell did not provide support for SSL, and we're going to need SSL support in order to connect to our Atlas cluster. So select Windows 64 and then download. Now, if you haven't previously accessed the Download Center, you'll be asked to complete a download form. Please just enter your details there and then move through to downloading the Windows MSI. Now we're presented with two options here, either Archive or MSI. Please select MSI. And again, it's Enterprise Server, Windows 64, and then MSI. And we'll just wait for that to download. And once it does, we can install. And once the MSI downloads, we can click it, and then use the installation wizard to install MongoDB. Select Complete, and then Install. Allow the app to make changes to our device, and then we finish. Now, it's important that you understand where MongoDB was installed on your computer. So if you click Windows Explorer, and then scroll down to Local Disk, on your machine, the download location should be something like the following: C:, Program Files, MongoDB server 3.4. And then if we click the 3.4 directory, we'll see that there's some license information, but most importantly is this bin directory. The bin directory contains all of the executables that are distributed with MongoDB server. The one we're interested in is Mongo. Now note that it's very similar in name to MongoD, which is the executable for the MongoDB server. For this course, we will be using the Mongo shell, which is run from the Mongo executable. Okay, before we can run Mongo, we're going to need to open a command shell. Now, regardless of whether you're working on a Windows 10 machine or an older version of Windows, you have a text box you can type in. And if you type cmd, you'll note that the command prompt is suggested for us. If we hit enter, then what pops up is a command line interface from which we will execute the Mongo shell. Again, the Mongo shell is a text-based environment. I can do something very similar on Windows 7 by clicking the Start button, and then in the search box, typing cmd and hitting enter. And again, I get a command shell that pops up. Switching back to Windows 10, everything I do here, you can also do on earlier versions of Windows, such as Windows 7. The command shell is largely the same in most versions of the Windows operating system. At least it's the same for our purposes in the ways that we will be using it. So if you take a look at what's been printed in the shell, you'll see it says C:\users\Shannon. This is simply a folder in the file system for my Windows machine, and I can find that folder if I look in C:\users\Shannon. So C:\users\Shannon is exactly this folder, C:\users\Shannon. Now, if I want to run the Mongo shell, on many versions of Windows, I need to do one additional step, and that is I need to set up my path. If you've never done this before, don't be worried about it. It's a pretty straightforward process, but it is down in the weeds a little bit, so we'll take it one step at a time. So to do this, I can type system environment, and just to be complete, variables. And long before that, Windows will have suggested this operation, edit the system environment variables. If I click on that, what I'll see is a window that pops up for system properties, and the advanced tab is already selected. If I click environment variables, then you'll see that I have user environment variables for Shannon and system environment variables. The one we're interested in is this one, path. And if we select path and click edit, we'll see a list of folders. These folders contain executable files or programs that can be run on this Windows machine. Now, on Windows 10, it's probably not strictly necessary that we update the environment variables, but on many versions of Windows, it is necessary, so I'm going to show you how to do it here. Now, as we said previously, MongoDB is installed in C:\program files, MongoDB, server, 3.4, and all of the executables are in the bin directory. So again, that's C:\program files, MongoDB, server, 3.4, bin. The way that that folder structure is represented in our path is by separating each component of the path with a backslash. So for our path, that looks like this. C:\program files, \MongoDB, \server, \3.4, \bin. Finally, what I'd like to do, before we finish editing this environment variable, is move this to the top. In order to understand why I wanted to do that, let's talk a little bit about how the path is used. When I'm in the shell and I type a command, like Mongo, again remember, Mongo is the name of the Mongo shell executable, Windows will look for programs with that name in each one of the folders listed here. And it does so in order. So it will first check this path to see if there are any executables located there. In this case, it will find one called Mongo and execute it. The reason why I wanted to place the MongoDB installation directory first is just in case you have an older version of MongoDB installed. because if you have an older version of MongoDB installed, chances are it's in your path, and you might accidentally end up running that version of the Mongo shell instead. Again, earlier versions of the Mongo shell did not include support for SSL, and we need that here, so we really need to be running the latest version of the Mongo shell, which you can download from the MongoDB Download Center as part of the MongoDB Enterprise package. So we can click OK here, and now you'll note that our path has been updated to include that individual path that we just added, and it's added at the front. And note that it's separated from the next item in the path by a semicolon here. And this is one of those difference points from Windows 7. And by that I mean, in editing a path in Windows 10, you have this nice list of items in your path. In Windows 7, it's a little bit more arcane, for lack of a better word, because in order to change the environment variable, we actually need to edit a string that includes all of the components of a path in one line. So here I can do exactly the same thing, system, environment, and before I'm even finished typing, Windows is suggesting the right thing to me. I click on it. Again, it's System Properties, Advanced tab selected. I click on Environment Variables. And then if I scroll down here, I can open my path and edit. And see here, this is what I mean. We just have one line of text. These are all of the same elements of the path that we saw in Windows 10, but rather than being on separate lines, they're all in one line. In order to update a path using this older UI, I can copy in my program files MongoDB server 34 bin path, and then type a semicolon so that it is separated from the next item in my path. With that, I can click OK, 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 and then I've updated my path on Windows 7. Returning to Windows 10, I want to do the same thing, click OK, and then what I want to do is restart the command prompt. Because on many versions of Windows, it's only after I restart the command prompt that those changes I made to the path environment variable will be reflected. So I'm going to close that, and I'll just start it the same way, typing command and then hitting enter. And now I'll be able to execute the Mongo shell. So to verify that we've installed it correctly and that we've set up our path correctly, what I'm going to do is type mongo --nodb. Now, --nodb simply means that we're just starting up the Mongo shell without attempting to connect to any MongoDB database. We're doing this simply as a means of verifying that we've installed the Mongo shell correctly and that we've set up our path correctly. And if you see a message such as this, MongoDB shell version 3.4.6 or later, depending on when you're actually doing this install, as we roll out the next version of MongoDB, your version number may change, but you should see a message very similar to this. You have successfully installed the Mongo shell and launched it correctly. To quit the Mongo shell, you can simply type quit. You can run the function quit, and that's it for installing the Mongo shell and getting set up to do a number of different CRUD operations in the Mongo shell. For the sake of completeness, I'll do the same thing in Windows 7. So I close the command prompt, launch it again, and run mongo --nodb. And here we can see that we have a slightly different startup message. This is pointing you to documentation and to Google Groups where you can ask questions. Before we close out, I want to say one last thing. If for any reason you have trouble installing MongoDB, please visit the MongoDB documentation for installing MongoDB Enterprise on Windows. This is a simple Google query away, and there's extensive documentation for how to install MongoDB on Windows. You can, of course, also ask for help in the discussion forum. But before posting, please make sure you do a search in the forum to see whether your question has already been asked and answered. Compass doesn't yet fully support the MongoDB query language. So in order to explore all CRUD operations in MongoDB, we're going to need to install the Mongo shell. The Mongo shell is a text-based client that we'll be using by means of whatever command line interface you have available to you on your system. In this lesson, we'll take a look at how to install the Mongo shell on a Mac OS X system. If you're on Windows, please see the video for installing the Mongo shell on Windows systems. Now, to install the Mongo shell, we're actually going to go ahead and just install all of MongoDB Enterprise Server. Enterprise Server is bundled with a number of executables that are part of the MongoDB ecosystem, including the Mongo shell. So please visit the MongoDB Download Center. You can get there with the simple Google query. Click the Enterprise Server tab, and then select your operating system. In this case, we want to select OS X 64. Now please follow these installation instructions, even if you already have a version of MongoDB installed. Earlier versions of the Mongo shell did not support SSL, and we need SSL support in order to connect to Atlas clusters. Once you've selected your operating system, click Download. Now, you might see a contact form pop up. If you do see a contact form, please complete it and then download Enterprise Server. Once the download completes, we can open the Finder and navigate to Downloads. Here's the file we just downloaded. I'm going to move it to my home directory. Now, if I navigate to my home directory, we can see the file right here. I'm going to double-click it and unpack the archive file. Then if I look inside this folder, I can see that there is, in addition to some licensing information, a bin directory that contains a number of executable files. The executable file we are interested in is this one, Mongo. This is the executable for the Mongo shell. Please don't confuse this with MongoD. MongoD is the executable for the MongoDB server itself. So when we say that we have a MongoDB deployment running, it's running one or more MongoDs. Again, we're interested in the Mongo shell or the Mongo executable. Please place the download that you've unpacked into your home directory. As I've done here, that will make following these instructions a little simpler. Now, in order to conveniently run the Mongo shell, we're going to have to update our path environment variable. The path tells OS X where to look for programs that we'd like to run. You can set your path in a hidden file called .bash_profile. If I open up Sublime Text and select Open, I can see hidden files on my Mac by typing Command-Shift-. Then if I navigate to my home directory, I can see that there is in fact a .bash_profile. Now, on your system, you might not have a .bash_profile. If you haven't created one previously, you probably don't. Don't be alarmed if you don't see one. You can easily create one by simply creating a new file in your favorite text editor and then saving it as .bash_profile. Make sure that you save it in your home directory. Don't save it on the desktop. Don't save it anywhere else. Make sure you save it in your home directory. You can simply click Save, and a .bash_profile file will be created for you. I already have one, so I'm simply going to open the one that I have. Again, it's Command-Shift- to see hidden files, and there's my .bash_profile, again in my home directory. If I open this, we can see that there is one bash command in here. This command sets the prompt for my terminal application. Now, in order to use the Mongo shell, we're going to run it from a command line interface. The terminal application ships with Mac OS X, so that's the one that I'm going to use. And one thing I'll point out here is that you can see my prompt is $ and then a space. That's because my bash profile specifies that the prompt for terminal or for any bash shells should be $ followed by a space. A dive into bash, a dive into using command line interfaces other than the Mongo shell is a little bit outside the scope of this course. So if you'd like to dive deeper on this, there are any number of tutorials on bash and the terminal application, or if you're on Windows, the command shell or PowerShell, any number of tutorials available online that I would encourage you to take a look at. So in order to run the Mongo shell conveniently, we want to set up our path environment variable. When you have a terminal application open, at any point, you can look at environment variables that have been set. For example, if I'd like to see what PS1 is, I can do that simply by typing echo $PS1. You must use the dollar character in order to stipulate that you want to see the value of that environment variable that's defined. I can do the same thing with the path environment variable. And here, I can see that it is set up to some standard system directories where executable files or programs are found. This is so that I can run a number of commands from the terminal, including a number of system programs that make the command line interface really work for me. What I'd like to do is update our path to include the location where we just put MongoDB. As a reminder, that's in my home directory under this folder and inside the bin subdirectory. Now, I've got an existing path. That's all of this. And I don't want to blow that away, so I need to make sure that in updating my path, I maintain all of those directories as well as part of the path. The way we do that is through a command like this. So here I'm saying, as the value of the path environment variable, use this sequence of directories. So this simply means my home directory, and then within my home directory, that long download name for MongoDB. And just as a convenience, don't try to type it because you'll probably screw something up. Just right-click and select copy, and that will copy the name of that directory for you. And then you can easily paste it in. So my home directory, the name of the download /bin. Okay? And then you'll see that I have a colon here. That colon says everything that follows is another directory in which to look for executable programs. So what this is saying is anytime that a user requests to run a program, look for that program first in Shannon's home directory, MongoDB-OS10-x86_64-3.4.6/bin. So look here first, and then if you don't find it there, continue on looking in other directories. Now, by specifying $path here, don't forget the dollar. What we're saying is take all of these directories, note that they're all separated themselves by colons, and put them here. The path is always searched in order, so this will be searched first, and then each of the directories that are listed following this directory, following this colon, will be searched in sequence afterward. I'm asking you to put the directory we just downloaded first in your path so that if you happen to have a prior installation of MongoDB, when attempting to run the Mongo shell, because the first place the system will look is in that directory we just downloaded, that is the version of the Mongo shell that will be run, not some version that you installed previously. So if we save this, then our bash profile is updated with a new path. The last thing that I need to point out about this is that your path in the terminal won't be updated until the next time you launch a terminal or unless you run a special command. So if I echo $path again, we'll see that it's exactly the same as it was before. However, if I type source /bash_profile, what that does is reads my bash profile that I just updated. And then if I echo $path, now we see that that new directory we added is included in the path. What this does for us is ensures that all of these executable files can be found if we type their name here in the shell. So now, if I type Mongo, and I'm going to add the --nodb command line option, and you see that? What happened is exactly what I cautioned you against, and that is that I haven't correctly specified that folder in which our downloaded version of MongoDB exists. So I'm going to go back into the Finder, and I'm going to select copy And then I'm going to go back into Sublime, and I'm going to update my path with the correct value. I'm going to save it, and then I'm going to source bash profile again. And now if I check my path, we can see that it's been updated correctly. And now, if I run Mongo, I can see that it does in fact start up for me. What we've walked through here is how to download MongoDB Enterprise package. We've talked about the fact that the Mongo shell is bundled with the Mongo server and a number of other executables. We've walked through how to set up our path environment variable so that we can run the Mongo shell from anywhere. And I've cautioned you against a couple of things that can go wrong when we're trying to set up the path. So it turns out that, given the steps we've followed, we actually have both the correct version and the incorrect version here in our path, because we were simply concatenating whatever was here onto the front of what was already the path. But don't worry, because if I simply start up a new shell, you'll see that just the correct one is there. So on new invocations of the terminal application, I'll pick up exactly what I want from my path, and I'll be able to run NoDB. We look at a few more tips about how to use the terminal application and go a lot deeper into how to use the Mongo shell in other lessons. One last thing before we close this lesson is that if you have any trouble at all installing MongoDB on your OS X environment, please visit the MongoDB documentation for detailed instructions on installing MongoDB Enterprise. In addition to OS X, there are detailed instructions for installing MongoDB Enterprise on Linux and all the various flavors of Linux, and on Windows. And again, the Windows installation is covered in another lesson.
It's easy to load data into MongoDB. In part, this is because MongoDB supports a very flexible data model, meaning you do not need to define a schema in advance or set up any tables. Tables, by the way, are called collections in MongoDB. In addition, MongoDB is flexible about the shape of individual documents within a collection. The number of fields, specific names of keys, and value types can vary from one document to another within the same collection. In general, you should develop and use a consistent data model, but MongoDB makes it easy to use an exploratory, iterative approach to developing the data model. This is important in nearly all use cases for data science. Requirements evolve, and the availability of new data sources imposes changes on our data models. So let's get started with an example of loading, cleaning, and iterating on a data model using MongoDB. First, we're going to load some data into your free tier cluster. For this, we're going to use the Mongo import program and import a CSV file of the data for a little more than 46,000 movies. First, download the file movies_initial.csv from the handouts. Then, we will import the data using the Mongo import command. Mongo import is distributed with MongoDB. Since you've already downloaded and installed MongoDB, you have access to it from the command line interface of your choice. On a Mac or Linux machine, you'll probably use a bash shell of some kind. On Windows, you'll probably use the command prompt or PowerShell. For this example, we're going to use some movies data from the Open Movie Database, also known as OMDB. This dataset is nice because it is large enough and requires enough data cleaning to be realistic. In addition, there are a number of other publicly available datasets that we can work to integrate with the OMDB data in a manner that effectively simulates the types of challenges we face in developing and maintaining data resources to support enterprise analytics applications. To import our initial dataset, you'll use Mongo import, specifying several command line options. Here is the template for the command you'll use. You simply need to fill in the command with the cluster name and seed list for your free tier cluster. To get this string, go into Atlas, and from the cluster view, click the Connect button. In the modal that pops up, select Connect with the Mongo shell. Mongo import has a slightly different API than the Mongo shell, so we just need to copy a couple portions of this connection URI. First, we'll copy the cluster name. The cluster name for your replica set should appear as the value for the URI parameter replica set. Go ahead and copy and paste it into our Mongo import command, replacing the cluster placeholder with the actual cluster name. Next, we need to select the seed list from this URI. The seed list begins immediately after the : / in this URI and ends just before /test. The seed list is nothing more than a list of the fully qualified domain names plus the port on which MongoDB is running for all the servers in your MongoDB cluster. Replace the seed list placeholder with the seed list you've just copied. See the lecture notes for this lesson for a Mongo import template command you can copy and paste, and for a written version of these instructions. Once you have correctly added your seed list to the Mongo import command, go ahead and run it. But before you do, make sure that the movies_initial.csv file is located in the same directory from which you're running the Mongo import command. I can run exactly the same command in Windows from the command prompt or the Windows shell. Mongo import has the same API regardless of which operating system you're running on. Once Mongo import finishes running, you should see a message indicating how many documents were imported. Now let's view the data we just loaded. For this and a number of other tasks in this course, MongoDB Compass is the best option. Compass is a GUI client for MongoDB that enables you to view databases, filter data using queries, modify data as needed, and much more. To download Compass, let's visit the MongoDB Download Center. I will just Google for it here. Click the Compass tab, and make sure you select the right distribution for your operating system. I'm running on a Mac, so I will download the latest version for OS X. Once downloaded, go ahead and install Compass. It should launch upon install, but in case it doesn't, just use Spotlight to launch it. Compass should also launch once installed on Windows. But in case it doesn't, just click Search and type Compass. Once launched, you'll see a Connect screen similar to this. Now, Compass is actively developed, so exactly what you see in the Compass UI might differ from what it is as I record this video. To connect to your free tier cluster, visit the cluster page for your Atlas account. Click Connect, and click Connect Your Application. Go ahead and copy the URI connection string, and then go back to Compass. You should see a modal that asks you whether you want to use the connection string you just copied to connect Compass to a MongoDB cluster. Go ahead and do this. Compass will populate nearly all the fields in the connection form. You just need to type the password for our analytics user. Remember, that is analytics-password. Now, all of the details you need to fill in this form are included in the lecture notes for this lesson. So don't worry if Compass didn't pop up the modal asking you if you simply wanted to copy in what was in the clipboard. At the very bottom of the Connect form, enter Analytics Free Tier and click Create Favorite so that you can easily reconnect to your free tier Atlas cluster at any time. Now I'll click Connect, and you'll see that I'm presented with 3 databases. The admin and local databases are created by default and are used by MongoDB for internal bookkeeping. The database we created when we loaded the dataset using Mongo import is called mflix. Click mflix. You then see that the mflix database contains one collection called Movies Initial with 46,014 documents in it. In MongoDB, documents are like rows in a relational database, and documents are organized together in collections, much in the same way that rows make up tables in a relational database. Each document in a collection is a distinct record. In the Movies Initial collection, each document stores data for one movie. Now, click Movies Initial. In the Documents view that loads, you can scroll through the documents in this collection. Note the fields and basic shape of the documents. In the coming lessons, we'll be doing some data cleaning and reshaping of the schema in order to better enable an application and analytics. For example, note that the genre field is a simple string containing a comma-separated list of genres. This makes it difficult to partition documents based on the genre. We'll do something about that and a number of other fields. There are a number of ways we can work with data in MongoDB. As we've just seen, One way is through Compass. In addition to simply viewing a collection, we can also filter and perform a number of other operations. Here I'll filter for the movie The Big Short. Note that just 2 documents from this collection match this filter. In fact, this is actually evidence of some dirty data because one of these is a duplicate. So we can delete the dupe. We can also update an individual document by editing its fields. Here I'll update this doc with the runtime. From a Google search, I happen to know that it's 130 minutes. So Compass provides a convenient means of exploring data, and it's visual. So that helps immensely in investigating many types of questions you might have about a dataset, especially as you first begin to work with it. But the bulk of the work will be in manipulating and analyzing data. For that, we want to use a combination of the MongoDB aggregation framework and query language. In this chapter, I'll provide you with an introduction to both as we work to reshape and clean up the movies dataset and integrate it with other data sources that will set us up to build an application and analytics infrastructure. We'll do all of this from Python using the MongoDB driver PyMongo. The same principles would apply across Java, Node, C#, R, or any of the other programming languages MongoDB supports. First, however, it's valuable to discuss how all the pieces work together. And I wouldn't be doing my job as an instructor if I didn't throw at least one architectural diagram your way. As you know, your MongoDB free tier cluster is running in Atlas. Atlas is a convenient platform for running MongoDB, which is why we're using it for this class. You could just as easily run MongoDB from your local computer, but Atlas requires very little setup on your part, and all the administration is managed for you. Depending on where you are in the world, your cluster is probably running on servers physically located in an Amazon AWS data center. This means it's in the cloud. I've drawn your MongoDB cluster as 3 servers because that's what it is. It's a replica set, meaning that 3 servers are working together to remain in sync, each maintaining a redundant copy of your data. One member of a replica set is always primary, meaning that it's the one you are communicating with when writing data, and usually when reading data. If the primary stops functioning or loses its internet connection, another member of the replica set will step in to serve as primary. Since it holds a complete copy of your data, you probably won't even notice if this happens. By default, both Compass and PyMongo are designed to direct their requests to whichever node in a replica set is primary, even if the primary changes. For a course like this, it's less important, but in production environments, this type of high availability is essential. The free tier option in Atlas supports this because a 3-member replica set is the default minimum deployment for all clusters in this platform. Now, you downloaded Compass to your local computer, so it's running there and connecting to your Atlas cluster through an internet connection. We will also be developing scripts and applications written in Python that will use your free tier cluster. In order to connect to MongoDB and make use of the aggregation framework and the MongoDB query language, we need to use PyMongo. PyMongo is available in PyPI, and you can install it using pip or easy install. PyMongo is just a Python library like many of the others you're accustomed to using, such as NumPy, SciPy, or Pandas. We'll also be making extensive use of Python Jupyter notebooks in this class to enable you to work through exercises right in your web browser. These will also make use of PyMongo, but that will all be handled behind the scenes in the Coursera platform. And that about wraps it up for the big moving parts of the scripts and applications we'll be using in this class. For many coding examples and exercises in this class, we're going to make use of Jupyter notebooks. These provide a convenient means of developing and running Python scripts without the need to leave the browser. To connect to your free tier cluster from a Python application, we'll use the Python MongoDB driver, PyMongo. Drivers are simply client libraries. In this case, a Python module that provides an API for connecting to and querying MongoDB. We'll go into quite a bit of detail about using PyMongo to connect to MongoDB and using MongoDB's rich query language and built-in analytics tools. We'll cover everything you need to complete this course, but if you'd like to dig deeper, I encourage you to take a look at the PyMongo documentation. See the link in the lecture notes for this lesson. To connect to our free tier cluster, first we'll need to import the Mongo client class from PyMongo. This class enables us to establish a client connection to MongoDB. Next, I need to actually connect to my free tier cluster. We do that by instantiating a Mongo client object. This is almost right, except I need to specify what MongoDB server I want to connect to. To do this, I need to go back into Atlas and copy the connection string for my free tier cluster. You'll need to do the same for your own cluster. Once again, I copy the URI connection string for connecting my application. As you know, this connection string contains the seed list identifying all the servers in my free tier cluster. PyMongo will keep track of which of the servers in my cluster is the primary, and direct reads and writes to that server by default. If it loses contact with the primary, it will communicate with the other servers in the cluster in an attempt to determine if one of them has stepped up to be primary. In this way, automatic failover happens to enable us to continue accessing our data even if we lose access to one or more of the servers in our cluster. Note that there are two placeholder values in this connection string. These are the password and database components of the string. Note that the username appears immediately after MongoDB://. Note also that the username is followed by a colon. The username is analytics. This is the administrative username I supplied when creating this cluster. Remember that the password is simply analytics-password. While the specific seed list for my cluster is different from the one for yours. In order to connect a Python application to your free tier cluster, you'll need to follow a similar process to what I'm doing here. The other placeholder in this connection string is database. I'm just going to replace database with mflix, since that's the name of the database into which we loaded the movies_initial collection. Okay, with that done, let's run this to test whether or not we've been successful. You can see that no errors were raised, and that based on the output of the call to print, we have a valid MongoDB client instance. Let's dive in now and start working with some data.
All right, welcome to our discussion of MongoDB's aggregation framework. The aggregation framework is a set of analytics tools within MongoDB that allow you to run various types of reports or analysis on documents in one or more MongoDB collections. The aggregation framework is based on the concept of a pipeline. The idea with an aggregation pipeline is that we take input from a MongoDB collection and pass the documents from that collection through one or more stages, each of which performs a different operation on its inputs. Now, each stage takes as input whatever the stage before it produced as output. And the inputs and outputs for all stages are documents, a stream of documents, if you will. Now, if you're familiar with pipelines in a Linux shell, such as Bash, this is a very similar idea. Each stage has a specific job that it does. It's expecting a specific form of document and produces a specific output, which is itself a stream of documents. At the end of the pipeline, we get access to the output, much in the same way that we would by executing a find query. And by that, I simply mean we get a stream of documents back that we can then do additional work with, whether it's creating a report of some kind, generating a website, or some other type of task. Now let's dive in a little bit deeper and consider individual stages. So an individual stage of an aggregation pipeline is a data processing unit. As I mentioned, that stage takes a stream of input documents one at a time, processes each document one at a time, and produces an output stream of documents, again, one at a time. Each stage provides a set of knobs or tunables that we can control to parameterize the stage to perform whatever task we're interested in doing. So a stage performs a generic task, a general purpose task of some kind, and we parameterize the stage for the particular set of documents that we're working with and exactly what we would like that stage to do with those documents. These tunables typically take the form of operators that we can supply that will modify fields, perform arithmetic operations, reshape documents, or do some sort of accumulation task, as well as a variety of other things. So finally, the last thing I'd like to mention about aggregation pipelines is that it's frequently the case that we'll want to include the same type of stage multiple times within a single pipeline. For example, we may want to perform an initial filter so that we don't have to pass the entire collection into our pipeline. But then later on, following some additional processing, want to filter once again using a different set of criteria. So to recap, pipelines work with a MongoDB collection. They're composed of stages, each of which does a different data processing task on its input and produces documents as output to be passed to the next stage. And finally, at the end of the pipeline, output is produced that we can then do something with in our application. In many cases, it's necessary to include the same type of stage multiple times within an individual pipeline. In subsequent lessons, we will look in detail at the various pipeline stages, what they do, and how to prioritize them. We'll also look at a number of different examples of building aggregation pipelines.
So let's dive in and start to explore this data using the aggregation framework. We'll look at what work lays in front of us in order to transform this dataset into something we can work with. In terms of differentiating audiences, one factor is going to be the language of a film. Ideally, it will be easy to segment movies based on language. So let's see what languages are represented here and what cleanup is going to be required. Here I have a simple script that makes use of the aggregation framework to summarize the values in the language field. What I'd like to do first is run this so that we can look at the output as part of the explanation for how this works. In order to run this for yourself, you will need to plug in the connection URI for your free tier cluster. Note that this is the connection for mine. You'll need to plug in the connection URI for yours. Now let's run. And you can see from the output that there are many movies in multiple languages. But it immediately occurs to us to ask, how many are there in this mix of languages? Do we really need to deal with all of them? The other issue that might pop out at you is that the languages are simply comma separated within a single string for each movie. This makes it difficult to filter on, regardless of the database you're using. Since this is our first aggregation, let's discuss the syntax before we go further. We can then return to the issues we've just identified. Here we have a group stage. The identifier for a stage always begins with a $sign. Group is no exception. A group stage groups its input documents by a specified identifier expression and applies any accumulator expressions supplied to each group. This identifier expression stipulates that we want each group produced to be identified by a dictionary containing a single field. The key for this field should be the string language, and the value should be a distinct language value. This type of expression in the MongoDB aggregation framework is a field path identifier. This identifies a particular field in input documents. And the semantics of this are that it's the value of that field that should be used where this placeholder is found. So for every distinct value of language in this collection, this pipeline will create a group and apply the specified accumulator to this group. Using a dictionary, labeling each of these distinct values with what they represent, that being language, ensures that the semantics are clear. The value around which each group was created is clear, and it's also clear that the value reflects a language designation. This is important, especially when the output contains a variety of results. As you know, an aggregation pipeline passes documents from one stage to another. This group stage is at the very beginning of our pipeline, so it will be applied to the collection on which the aggregate command is run. In this case, aggregate is being run on our movies_initial collection. Each document in the collection will be passed through this group stage. Group stages allow us to apply any number of accumulators that operate on the documents passed through the stage. $sum is one such accumulator. This expression means that for every document matching the identifier for a group, add 1 to a running count of the documents grouped around that identifier. There are a number of other accumulators, many of which you will encounter in this Coursera specialization. Here is the MongoDB document page that describes the available accumulators. There are several others for arithmetic operations, several that work with lists or arrays, and a couple that enable you to calculate descriptive statistics. Now, one big advantage of the aggregation framework is that all the work is done within the database server, which has been optimized for the operators the aggregation framework supports. This, combined with indexes that support extremely fast lookup operations, means that using MongoDB in this way makes for a very powerful data manipulation and analytics toolset. Returning to our example here, once all input documents have been processed through this group stage, the stage will emit as output one document for each group. Each of those documents will contain two fields, an _ID field, specifying the distinct value for a language that group represents, and a count field that contains the number of documents in that group. Since this group stage is both the first and the last stage in this pipeline, it is the output from the group stage that we receive as output from the entire pipeline. The last statement in this script is our call to the aggregate method. Note that we're using our client connection to access the mflix database attribute of this connection and the movie's initial attribute of the mflix database. Finally, we're calling the aggregate method of movies _initial. Aggregate is a collection class method. And to aggregate, we're passing a single argument, the pipeline that we've constructed here. Note that the pipeline is a document, or more precisely, because this is Python, the pipeline is a dictionary. Just two other things I want to point out. I'm using the pprint package so that we can print out nicely formatted output. And because we're using Jupyter Notebooks, I'm importing this clear output function so that we can run this as many times as we like, and each time the prior output will be cleared for us. Given the way we've structured this pipeline, the result is the output of hundreds of documents, each representing a distinct value for language, and the count of the number of documents in the movies _initial collection that have that value for language. This isn't as useful as it could be, and doesn't address our question of how many distinct document values there are in any real useful way. In order to do that, we'll need to expand our pipeline with a couple more stages. We can get a clearer picture of this data if we sort the results. Sort is just another pipeline stage. As with group, we identify the stage by its name, $sort. The expression used to define the sort is a dictionary. This document should specify the field or fields we want to sort on. Use 1 to indicate you want to sort in ascending order. Use -1 for descending. In this pipeline, the $group stage emits documents that contain just two fields, _ID and count. We are sorting on the count field. Let's run this. Now, in scanning through these results, we can get a sense for the variety and relative frequency of language combinations used. So what we've done here is grouped in order to count and then sorted on the count. This is a very common sequence of operations, so common that the aggregation framework actually includes a single stage that supports this idiom. It's called sort by count. So we can simplify this pipeline to just this. The thing I love about this is that we're able to perform an important operation with very little effort. There are a number of examples of this type of power throughout the aggregation framework.
The problem with this output is that it doesn't provide a very good summary of what values the language field holds. Using this movies data might require a deeper understanding of, say, how the languages are distributed. In general, understanding the distribution of data in a field is valuable as part of any ETL process. This is one example of an ETL problem, and my objective is really just to give you a taste for what's possible with the aggregation framework as we begin this specialization. We have quite a few fundamentals to get through in this course, as you ramp up on the MongoDB ecosystem. And in the second course, we'll do a deep dive on the aggregation framework. Returning to this example, let's generate a better summary of the distribution of values in this field. Essentially, I want to see specifically what language combinations are heavily used and just get a sense for how many unique language combinations we're dealing with. I want two different types of summary information. One has details on specific language combinations. The other just provides some raw counts. I can do this in Python, but it would require me to write a couple dozen lines of code and would be a little slow because I'd need to process all the documents in my script rather than in the database server. The challenge doing these two types of analysis simultaneously presents to the aggregation framework is that with the pipeline, I can really only process the documents to one outcome. Again, this type of situation frequently arises, so the aggregation framework actually does support running multiple pipelines in parallel with the use of the $facet stage. Let's use a $facet stage to provide both types of summary information I want. Again, remember, I want details on specific language combinations and just some raw counts on unusual combinations. $facet enables you to define multiple pipelines through which to process the same input documents. The output for each pipeline is emitted as the value of the key you specify in the facet stage definition. Here, I'm using $facet to define two pipelines. Note that I'm defining two fields. Each has as its value an array, here and here. Each one of these arrays defines a separate pipeline that will be processed in parallel, and the result of running each pipeline will be stored as the value of these keys in the output from this $facet stage. These pipelines function just like a top-level pipeline. In this case, both pipelines will receive as input the stream of documents emitted by the sort by count stage in the main pipeline. I've defined one pipeline and labeled it top language combinations. The output of this pipeline will be emitted as the value for a key with this same name, top language combinations. This pipeline will simply take the input it receives from the sort by count stage and limit it to the first 100 documents. To do this, I'm using a pipeline stage you've not seen yet, but it's pretty straightforward. Just specify an integer as the value, and the $limit stage will take its input and pass those documents along as output until it reaches the limit you've specified. Once the limit is reached, it stops. The second pipeline uses two stages, skip and bucket auto. Skip, like limit, is defined by specifying an integer. And I see that I've actually got a mistake in my code here, because what I really want to do is skip all of those top language combinations in this pipeline, because I'm considering all of those to be unusual combinations. So I don't want 25 here, I want 100, because I'm considering the first 100 to be top language combinations, and for those, I'm simply calculating counts. So let me go ahead and fix this. And then, what I'm doing here will again take that output from the sort by count stage, skip the first 100, and then pass the remainder documents through to this second stage in the pipeline I'm defining here for unusual combinations. Now $skip, like $limit, is defined by specifying an integer. It simply ignores the number of input documents you've specified that it should skip. Once a number of documents equal to the skip value has passed through a skip stage, it will pass any additional documents on as output. $bucket auto is the second stage. It's very similar to the group stage, except it automatically defines a list of buckets into which it will group input documents. The buckets are defined by the value you specify for the group by key. Here we're using the value of $count as our value around which to group. However, rather than create groups based on a single value, Bucket Auto will automatically define ranges of values and group all documents that fall within that range into the bucket. We specify a cap on the number of buckets that will be created using the buckets key for the $bucket auto stage. Here we're asking Bucket Auto to create 5 or fewer buckets. For each bucket, it will output the value we specify for the output key. Here I'm saying that I want the value of each bucket to be a document containing a single field. The name of the field should be language combinations, and its value should be the count of the number of documents added to this bucket. As we did with $group earlier, we're simply using the $sum operator to add 1 to a running count for every document added to this bucket. Since the output of the sort by count stage in the main pipeline is a stream of documents that captures the number of movies that use a particular combination of languages, the output of the unusual combinations shared by pipeline will be a count of the number of movies that share their particular language combination with only a relatively small number of other movies. Those that share their combination with only 2 or 3 other movies might be grouped together, for example, depending on the distribution bucket auto sees and what buckets it creates. So let's go ahead and run this. In the output, we see that indeed, for top language combinations, we have a list of documents that specify the most frequently used language combinations as the number of movies in our collection that use that combination. So 25,000 for English, down to 16 movies that use a combination of English, Italian, and Spanish. A couple of other things to note here are that, not surprisingly, a small number of language combinations dominate the dataset here at the top. One other thing to note here is that a significant number of documents in this collection do not specify a value for language at all. That's why we see this empty string as one of the keys in our output. More than 1,000 documents have no value for language. As we scroll down and look at the output for unusual combinations shared by, first let me explain that bucket auto specifies ranges such that the minimum value is included in the range, but the maximum value is excluded. So for the second bucket, for example, we'll have all movies for which at least 2, but no more than 5 movies use the same language combination. In this first bucket here, we see that there's a large number of movies that use a language combination that no other movie does. Nearly 1,900 that use a unique language combination. So with $facet, we can see how we can perform 2 types of analysis simultaneously with an aggregation pipeline. And we've really just seen the tip of the iceberg. But this at least gives you a glimpse of how easy it is to perform some pretty complex exploratory analysis of datasets using the aggregation framework. Again, we'll dive into some deep data science using the aggregation framework in the second course in this specialization. Now that we've explored the dataset a bit, at least for one field, let's take a look at how to filter to get just those movies that match a particular criterion. There are several ways we can do this. Compass supports the MongoDB query language. There is a $match stage in the aggregation framework for filtering, and there is a collection method called find, which we can use from a Python application. All of these support the same filter syntax and set of operators. The one exception is Compass, which at this time supports only a subset of the MongoDB query language, though it is a very large subset. Let's do some simple queries in the aggregation framework first. The syntax for writing filters in MongoDB is based on documents. You specify one or more keys on which you would like to filter, and then for each key, provide an expression that defines the criteria that matching documents must meet for that field. As a simple example, let's search for movies that use both Korean and English. To do that, we'll use a $match aggregation stage. Have a look at the syntax here. There is an equality match on the language key. If you're building a Python application such as a web app, it's more likely that you'll use a query language method to filter documents. For filtering, you will most commonly use the find collection method. Let's take a look at an example. Here, we define a filter. Note that it's just the filter portion of the match stage we just looked at. Both the MongoDB query language and the aggregation framework use exactly the same syntax and operators for expressing queries. To apply this filter, we simply pass it to the find method. Remember that find is a method on the collection class, so here we're calling find on our movie's initial collection that we've been working with all along. Find returns a cursor that enables us to iterate the results. A cursor is simply a pointer to where we are in a list of query results. Calling list here causes Python to iterate through the cursor and create a list. pprint prints the output that we'll see when we run this script. And we can see here that what we get is in fact a list or array, and that every one of the results in this list does express a combination of Korean and English for the language field. We can do this same thing in Compass, and it uses the same syntax, or very nearly. The only difference is that Compass likes double quotes rather than single quotes. And applying that filter, we can see that the result set is reduced to 27 documents. And again, if we scroll through these results, we see that the combination of Korean and English is what's used throughout for the language field. This type of query is called an equality filter because we're matching on exact values for a key. As I mentioned earlier, we can filter on multiple fields. So to provide an example of that, let's go ahead and add an additional selector to this filter. And applying that filter, we can see that our result set is reduced from 27 to just 2. Because now we're requiring that all documents returned in our results set have a combination of Korean and English as their language, and a rating of unrated. Now, one last thing I'll point out about the MongoDB query language as expressed in Compass is that for keys, it is not necessary to use quotes. Compass will correctly interpret these as keys, and we get a slightly cleaner looking filter as a result. Of course, in Python, when constructing filters, it is necessary that you use quotes because you're really just building a dictionary that is passed to find as a filter. Now, I'd love to go further and show you how to do range queries on fields like runtime, and maybe even look at interesting combinations of genre, for example. But the fact is that this dataset is a bit of a mess. Values like runtime should be integers, and languages, genre, and several other fields should be arrays so that we have maximum flexibility with respect to filtering this collection for the types of analysis we need to run and for when we build an app a little later in this course. So let's take a look at cleaning up this dataset. Okay, so let's take this a step further. This is exactly the same pipeline that we looked at in the previous lesson. The difference is that we're now going to begin to do a little bit more sophisticated work within our project stage in order to handle some other problems with the data in this particular dataset. So here you can see the same pass-throughs and these split operations again. But for released, if we take a look at what we have for values in this collection, it's just a string. We can do quite a bit more in terms of range filters, searching for all movies released at a particular time of year, in a given month, etc., if we actually convert these to dates. So that's what we're doing here. Let me explain this a little bit. If it wasn't for the case that values could be empty, this would be significantly simpler. We would simply need to use the date from string operator to parse the date out of the string. But because we can have empty strings as the value for released, we need to use the cond operator. Cond is simply a conditional expression. We have an if, then, and an else. And because everything is document-based in MongoDB, we express this using this document-based syntax. So the cond operator has as its value a document, and that document has 3 keys within it, an if, a then, and an else. For if, we specify a conditional expression. And the conditional expression we're using here is making use of this $ne operator. $ne simply means not equal to. $ne expects an array as its value where we have 2 values to be compared. Here we're using this field path specifier to get the value for released, and we're simply saying if that value is not equal to the empty string, then we want to go ahead and parse the string from it. Otherwise, just go ahead and let released equal the empty string. So let's talk a little bit about the meat of this particular reshaping, which is really parsing the date out of a string. Date from string is an operator that expects us to specify the value we want to parse as an expression that evaluates to a string. Here we're using a field path specifier. So whatever the current value for released is, and we have to specify that as the value for date string. There are some other options you can specify to date from string. We're not going to talk about those right now, but that's why this has the structure that it does. The result here is that if the expression is true, then the value that will be assigned to the release key in this projection is the date value parsed using the date from string operator from the current string representation of that date, which is the current value of the released field. Otherwise, we simply make released have the value of the empty string. Again, as we build up this reshaping, we're just looking at the first 100 documents, and we are again outputting to the movies_scratch collection. So let's run this. And if we go into Compass and refresh, we see that now we have a real timestamp as the value for released for all documents that actually had some sort of string representation as their value. For others, we'll just have the empty string. But we can see several here that have had their released field updated to have a real timestamp, which we can then filter on in a variety of interesting ways. So that's an example of how we can do a little cleanup with respect to dates. Now, one other thing that I want to point out is date from string is an aggregation operator that is only available in MongoDB 3.6 and later. So if you're using an earlier version of MongoDB in your Atlas cluster, or in, say, a local installation that you have created, you'll need to upgrade to MongoDB 3.6 in order to take advantage of this particular operator. So continuing with the reshaping that we're doing here, as we did with released, let's parse a timestamp out of the last updated field. As we look at that field as it currently exists, we can see that there's a timestamp here, but it is encoded as a string. And it has some extraneous data here, in fact, that means it doesn't quite match some of the standard timestamp formatting that we're expecting. So what we'll do here is, using a conditional expression very similar to what we did for the released field, because again, last updated might be an empty string, we're going to rename the last updated, no capital U, to last updated with a capital U. But if last updated, the current value, is not equal to the empty string, we're going to parse a timestamp out of it. Now, we're going to use date from string again. And again, remember, the date from string operator is available only in MongoDB 3.6 and later. And we're specifying using a field path expression that we want to parse the current value of last updated. But we're also supplying an additional parameter to the date from string operator, and that is specifying the time zone. Here, I'm simply specifying that it should use New York time or US Eastern time. Now, there's one additional complicating factor here, and that is due to this little bit of extra data here after the dot. And it's not so much the fact that there's a little bit of extra data here after a dot, it's the number of digits that are here that's really causing us a problem. But the fact is, we don't care about milliseconds. Down to the second is good enough. But in its current form, date from string will not be able to parse this because the format does not match its expectations. So I need to do a little bit of pre-processing on this data. And I'm doing that here with the stage I'm introducing just before the project. So here what we're going to do is split on that dot that we see in those values. And then we're going to use an operator we've not seen yet called array_elem_at. Array_elem_at will select the value stored at a particular index within an array. And here, what we're doing is, as the value to array_elem_at, we're specifying that we're going to use as our array the array that we get by splitting on the dot character for the value of last updated. So here, this portion here will be the 0th element in that array, and this would be the element at index 1. Array element expects as a value an array. The first value in the array should be the array we want to index into, and the second value should be the index we're interested in within that array, or the element we're interested in. Again, we're interested in the element at index 0, and the semantics of this then will be such that last updated will be added to every document that flows through this stage, and it will have as its value the string that's found at index 0 after we split the current value of last updated, that string value. Okay, so one thing I didn't mention about add fields when we talked about it before is that if the field already exists, it will simply replace it. So what we're doing here is replacing the existing last updated field with a string that is just the left side, essentially, of a split that happens at this dot for every document in the collection. This is actually a good place to call out two things. One is that as you're building up an aggregation pipeline, it's a really good idea to test each stage individually. So what I did as I was building this particular pipeline was to end the pipeline here at this add field stage to make sure that the data was being split and created properly so that it would be passed as expected into the project stage. I'd encourage you to do that as an exercise for yourself in testing this a little bit and in getting familiar with the aggregation framework. That brings me to the second thing I like to draw your attention to, and that is that we're not doing a comprehensive deep dive of the aggregation framework here in this particular course. What I'm doing here is trying to whet your appetite with what's possible here, and we'll do a deeper dive in the second course in this specialization. Undoubtedly, you'd like to know a little bit more about the Ag framework, so I encourage you to take a look at the MongoDB documentation, in particular, this aggregation pipeline quick reference. It's linked in the lecture notes for this lesson, and here you can find information on all of the operators and expressions that we've been using throughout these examples. Here, for example, are the array expressions, and the array element operator is listed first. So, returning to our example, again, we're taking the output of the project stage, which now is going to parse a date from both released and last updated, and we are writing that data into the movies scratch collection. So let's go ahead and run this. And if we refresh in Compass, we'll see that now for last updated, we do in fact have a real timestamp, not just a string representation of a date time. In the same way that we can do data cleaning in the aggregation framework, we can perform those same operations using the MongoDB query language. Basically, the choice at this point in the development of MongoDB is whether you want to work in a declarative framework, like the aggregation framework, where you simply specify what it is you'd like documents to look like, or whether you prefer to script your cleaning operations as you're probably accustomed to doing in Python or another programming language. Either works. My intention here is to give you exposure to doing either of those so that whichever best suits your style, your needs, or maybe even just your interests, you have what you need in order to get started. For those of you who are keen to be up to speed on a variety of different options and would like to learn the aggregation framework, I strongly encourage you to dive in there and wring all the value you can out of the aggregation framework. The Ag framework is one of the most aggressively developed components of MongoDB because of its widespread use and utility for MongoDB's developer and data science communities. So we've taken a look at that. Let's look at using the MongoDB query language to do the same type of thing. So here I have a script. I'm importing PyMongo and the Mongo client class, and a few other utilities that I'm going to need, such as datetime and the regular expression library. The bulk of this script happens within this for loop. And the idea here is that one at a time, I'm defining updates for an individual document and then writing those updates to the database. We're going to do this through the use of the update1 method. This is a collection level method, and we'll be calling it on the movies collection. Now, for this particular script, so that I don't write any data in my movies_initial collection, I've actually loaded the same data into a different collection, because what we're going to be doing here is making a number of writes to the same collection rather than copying our updates to another collection. We're going to be making use of update1. For update1, we'll be passing 2 parameters. This is the most common way of using one of the update methods in MongoDB. There is a similar method called updateMany that allows you to update multiple documents at once. But in our case, we need to update one at a time. A little bit later on, we'll look at a way of updating a bunch of individual documents in batch so that we have a substantially more efficient operation. But for introductory purposes, I think it makes sense to begin with updating one document at a time. So the first argument to update1 is a filter that selects the document we wish to update. The _ID field contains a unique identifier for an individual movie in this collection. Here, this filter says, I'm interested in updating the document with the _ID value equal to the _ID of the document I'm currently processing in this for loop. And then this variable here, update_doc, is a reference to a dictionary or document that defines the updates that I want to make. So what I'd like to do first is run this script. And because of this statement here, we'll be able to see exactly what updates we will make to documents in this collection once they're issued. What I mean by that is that this will print out the value of the update_doc variable that we'll be passing to update1 each time through this loop. Now to run this, what I'm going to do is comment out the call, because I don't actually want to make the update. I just want to see what would happen. And once we've taken a look at the output, then we'll go back and talk about how this script works. Okay, so running this, let's take a look at the very first document output by this statement. Okay, remember, what I said is that we're building up an update document, a document that defines the updates we want to make to an individual document each time through the loop, and then calling update1 to write those updates to the collection, changing the document identified by this _ID value each time through the loop. All of these update documents will be composed of 2 keys, a $set key and a $unset key. In the MongoDB query language, for update operations, $set has the semantics of specifying a field that you either want to add to the document in question or a field that you want to update with a new value. In the case of the first document, you can see the kinds of updates that we're making. These should look very familiar to you because they are the same types of updates that we were making using the aggregation framework in our project stage. I'm writing arrays for cast, countries, and directors, as well as genres and 2 other fields. I'm changing the field name from full plot with a lowercase p to full plot with an uppercase p. I'm creating an IMDb key with an embedded document, and so on. Something new that I'm doing here is I'm eliminating a number of different fields. I'm deleting a bunch of different fields. So there's 2 reasons why I delete fields in each of these updates that I'll be committing to the database. The first reason is I'm getting rid of fields that use the singular form of the key. So I am writing a countries field here and deleting that old country key, and doing the same for the other 4 fields that required that type of change after I split their string values into arrays. These 3 values are being embedded in this document. And finally, the way this script works is I've defined it to delete all keys for which the value is simply the empty string. So rather than have a bunch of empty string values in the documents in my collection, I'm simply deleting those keys altogether. Remember that MongoDB has a flexible document model. It's okay to have documents that have a different shape in the same collection. It makes things a little bit more efficient for us. And through the use of the $exists operator, it's easy for us to identify documents that either contain or do not contain a particular key. So all of my update documents, that is, the values that I'll be passing here as the second argument to update 1, have this form: a $set field with a specific key and value that I'm assigning, and a $unset field with a list of fields to delete from the document. Now let's talk about how this script works. All right, so now let's talk about how this script works. Let's begin at the top of the for loop. Here we're using find, as we did previously, but the filter that we're passing here is an empty dictionary or an empty document. The semantics of this for MongoDB are that we expect to retrieve as results from this query every document in the collection. Now, here what we're doing is limiting it to the first 100 documents retrieved using the limit method. Limit is a cursor method. So find, as we know, returns a cursor, which allows us to iterate over the documents that are retrieved. Limit is a cursor method, which will restrict the number of results that we see to, in this case, the first 100. I could pass 1,000 here, I could pass 365. It just depends on what you need. Limit also returns a cursor. Now, doing so as part of a for loop means that Python will iterate on that cursor, and each time through, movie will be the next document in the collection. Suppose that we hadn't set a limit here, or that it was quite large, thousands and thousands of documents. PyMongo and MongoDB work together to do the right thing here, which is to return the documents in batches of many dozen. So with each batch, we have that many documents on the client side and are processing them. And as we get close to exhausting a batch, PyMongo will go fetch more documents from the server in another batch. And so rather than pull documents across from the server one at a time, we're pulling them across in batches. And that's how we end up looping through each of the documents in the collection. Now the next thing to look at are these fields to set and fields to unset dictionaries. In the body of this loop, this is where we are building those dictionaries that we see as the values for set and unset in the update document. So the first thing that I do here is loop through all of the fields, pulling out the individual keys and values for each document as we pass through the loop. If the value is some version of an empty string, then I remove it from the movie dictionary. Note that I'm using copy here so that I can do that without getting the dictionary change size error. I remove it from the movie dictionary, and I create an entry in the fields to unset dictionary for that key. That's how I end up with, for example, this Metacritic entry in the unset dictionary for this document, because there simply wasn't a Metacritic value for this particular document that I'm going to update. It was just the empty string. So I can save space and make my data a little bit more readable by getting rid of all that empty data. And then we dive into a block of code where I'm splitting string values into arrays. Note that for each one of these, I'm checking to see whether it actually exists in the movie dictionary, because if it was empty, if it was the empty string, I would have deleted it here. And note that for director, writer, genre, and so on, I'm specifying that that field should actually be eliminated as part of the update operation if it wasn't already eliminated here. And I'm saying let's add a field called directors in this case that is the array that I get by splitting that string value of directors. Likewise for writer, genre, language, country. Note that for cast, I do the split, but I don't unset the cast field because I'm using exactly the same name for the array version of that field rather than some plural form of cast. Here I'm simply changing the name of full plot so that it is camel case, and doing that same change here to use rated versus rating. This is the chunk of code that creates the embedded document. And here I'm converting string representations of dates to date times using the datetime class. Finally, this is one of the more interesting bits of this particular script. It's something we actually can't yet do in the aggregation framework. Here, I am changing the data type of runtime. More specifically, I'm really doing two things. I'm first running a match on runtime, because if you take a look at any runtime, you'll see that it's this ridiculous string of 1 space min, 6 space min, 190 space min. It's not an integer, so we can't do range queries. We can't do any of the types of analysis we'd really like to be able to do because it's a string, and a string that's in an inconvenient form at that. So here at the top, I've compiled this regular expression that will do a match and will group the different components of the match in such a way that I can pull out the integer component for that value. And then I simply convert it to an int here, and make sure that runtime gets added to the fields to set, so that here when I construct the update doc, that's one of the changes that will be made as we call update1 in order to make the necessary updates to this document. Now, something I want to point out here is that note that we're not doing anything with title, nothing with year, nothing with plot, nothing with any of these fields where we've just got a 1 here, where essentially we're just passing the value through. As long as there is a value other than the empty string, we're doing nothing with it. That's because to update, we only need to identify the fields that we want to change in some way, whether it's setting them to a new value or eliminating them from the document. Now, in this example, we're using just 2 of the update operators, $set and $unset. There are a number of other update operators. See the lecture notes for this lesson for a link to the relevant MongoDB documentation. I can increment values, I can take the min and max, multiplication, a number of operations with arrays, and a whole host of other types of updates that reflect the variety of different things we have to do when we're transforming our data from messy and somewhat ill-formatted to data that we can actually use. So take a look at the docs to see what else is possible in update operations. Lastly, I build my update doc from the fields to set and the fields to unset, those 2 dictionaries I've been building all along. Note that each one of these creates a new entry in either the fields to set dictionary or the fields to unset dictionary. That's how I end up with output that looks like this. Then if I were to run this, eliminating the limit and uncommenting my call to update1, I would, one at a time, update each document in the collection. Update1 is great when I'm updating a few individual documents. But when I'm trying to reshape an entire collection, this is not a terribly efficient strategy. I'm going to change this script so that I'm actually doing bulk writes rather than writing one document at a time back to the server. I'll show you how to do that in the next lesson. Okay, so let's talk about how to do this type of update the right way. What we're going to look at here is something called bulk writes in MongoDB. This is essentially a way of performing a number of update operations with a single request to the database. So rather than update each document one at a time, we're going to batch together updates for, in this case, 1,000 documents at a time, and then make a single request to the database for all 1,000 updates at once. So the update code that we see here is exactly the same as what we looked at in our lesson on the use of update1. The only difference is that, as I said, instead of calling update1, we are instead going to use this update1 class, which I've imported from the PyMongo library here. We're going to use update1, which is an operation class, to create an update1 operation object here and add it to a list of updates that we're keeping track of. Then, each time through the loop, we're simply checking how many updates we have accumulated to this point, how many update objects we've accumulated. And once we've hit our batch size limit, which as we saw above is 1,000, then I make a call to the bulk write method, passing it this list of updates. Take a look in the handouts for this lesson to study this code in detail if you have any questions. But the upshot is that we are creating 1,000 update1 operation objects, passing that list of update1 objects to the bulk write method. Bulk write will construct the necessary request to the MongoDB server, and the server then will receive that entire list of updates. It will then apply the updates one at a time. Again, the update code, the way we're selecting what document to update, and the specific updates to apply for each document are exactly the same as we looked at in detail in our lesson on the use of update 1. Here, we're doing exactly those same updates, but doing it in a much more efficient manner. Outside this loop, we have one statement here, and that's merely to catch the final list of updates that need to be applied, because it's entirely possible and in fact probable that we will finish this loop with some number less than 1,000 updates that need to be applied. In order to catch all of those, whatever remains, we call bulk write here if in fact our list does contain any updates to be applied. Okay, so let's actually test this code. And in order to do that, what I'm going to do is first create a brand new collection in my database that is the original movies dataset that we began working with in this course. So when I make this call to Mongo import, this will load that initial movies dataset into a new collection called movies in my database. Now I'm doing this just so I don't mistakenly update the movies underscore initial collection. So I'm going to go ahead and execute this. And once it finishes, then I can go into Compass and I can take a look at that dataset. And here we can see that it is in fact has the same shape, and this data should look very familiar to you. Now, let's go ahead and execute this bulk update code. And once that finishes, then if I look again at my movies collection, once the script has finished running, I can see that the dataset now contains arrays for all of the fields that I've split from strings into arrays. I have an IMDb embedded document. And as we scan through, we can see that there are no empty fields or fields that have as their value the empty string. And finally, for runtime, for each document, I have an integer. So that gives us a pretty good overview of how to go about doing data cleaning in a collection in MongoDB. We've looked at several different approaches, and in the process given you a pretty detailed overview of some of the key aspects of the MongoDB aggregation framework, as well as the MongoDB query language and use of the PyMongo driver in the Python programming language.
In this lesson, we're going to talk about the different data types that MongoDB supports. And we're really going to get into some of the different data types that MongoDB has. But not only that, we're also going to talk about how we can query for documents by the data type that a field is. So by now, you already understand that MongoDB stores data in documents, and you're already somewhat familiar with the different data types supported by MongoDB. For example, here I can go ahead and query for a random movie and print it out. And as you can see, we know that title is a string. We know that runtime is a number. We've also looked at more complex data types in MongoDB, like how cast is an array, or like how IMDb is actually an embedded document. But let's look at all the different data types that MongoDB supports. And here's a list of all the different data types supported by MongoDB on our documentation page. And we don't have time to talk about all these different data types, but in this lesson, we're going to talk about 3 of the most interesting. So we're going to talk about object ID, date, and finally we're going to talk about decimal 128. So coming back to our notebook, here's the random document that we found. We can go ahead and look at the specific _ID field. And you'll notice that it has this object ID wrapper around this random string of letters and numbers. And so this object ID is actually a MongoDB data type. And it's special because what it allows us to do is it allows MongoDB to identify uniquely every document in the database. And it's able to accomplish this because this random string of characters is actually composed of the current time in Unix, the ID of the machine that is running this, the process ID, and as well as a counter that starts with a random value. And through all of these different pieces, MongoDB is able to, with somewhat good certainty, ensure that this object ID is unique and is able to therefore uniquely identify every document in the database. And so that's object ID. Now let's talk about the date data type. So I can go ahead and import date time, and then I can go ahead and look at this example test collection that I've created called dates. So here's this dates database, and now I'm just going to go ahead and insert one document where I say DT, which is date time, is the current time right now. And so when I run this, you can see that it was successful, and now I should be able to find it right away. And so this is really cool. It's really awesome that MongoDB allows us to natively insert dates into MongoDB, because this allows us to query for dates in a lot more interesting ways. We can now query for dates using logical operators like less than and greater than, and a lot of other interesting things, like it allows us to use advanced aggregation operators that allow us to pull out different components of this date. Like I can figure out the day of the year that this date is, or I can figure out the year that this date is. And all this wouldn't be really possible if we were just storing this date as a simple string. And finally, I also want to talk about this really interesting data type called decimal 128. And so we already know that MongoDB allows us to store floating point numbers. But more than that, MongoDB also lets us store decimal numbers. And this is really important whenever you're storing numbers that represent something that has to be strictly precise and strictly represented. And a great example of this is money. So we don't want any rounding errors when you're doing math with money. And so when we are using money and storing it in MongoDB, we really want to use the decimal 128 data type so there's no rounding errors. And so MongoDB natively supports this. And so we can go ahead and import this special data type from the bson library and then insert a document. Pretty simple. The API is very simple. You just wrap your number as a string and then wrap that in the decimal 128 function. And then as you can see, we successfully inserted it, and now I can easily find it. And you can see that this is stored kind of exactly as the way we would expect. MongoDB is powerful not only because it lets us store data with this rich variety of different data types, but also it's really cool because we can actually query for documents based on their type. So in this case, you can see here, I'm writing a query where I want to find movies where the year is of type integer. And so when I run this, exactly as we would expect, here I'm able to find a movie where the year is an integer. And this is useful for two common use cases. Firstly, this can be useful when we want to clean our data. We can use the $type operator to find that every field is the exact type that we expect it to be. But second, this can be very useful if we have a schema where a field has multiple data types across documents. For example, maybe we store the director field as a string if a movie only has one director, but we store it as an array if it has multiple directors. In that case, we could use the $type operator to find movies of that specific type, whether it be string versus array, and go from there. So let's go ahead and recap what we discussed in this lesson. We saw a list of all of the different data types in MongoDB, and specifically we talked about three special ones. We talked about object ID, we talked about date, and finally we talked about decimal 128. And then we saw that we can actually query MongoDB based on data type, which is useful for cleansing data, and it can also be useful when we have documents with different types for a field across multiple documents.
Viewing the new collection we've created here in Compass, let's search for movies that use the Korean language. Note that we need to use the key languages. With this filter applied, we have 542 matching documents. Let's take a look at some of the matching documents. The first has both English and Korean listed for languages. And if we scroll down a bit, we can find a movie that has just Korean listed as the language. And if we scroll down even further, this movie lists 5 languages, including Latin. So let's stop and think about what's happening here a little bit. First, we've simply filtered on the movies collection using exactly the same syntax as we would if languages were a scalar field. For example, a field containing string values rather than array values. The difference is that now we're not relying on a string representation of a list of languages. We can take full advantage of MongoDB's support For array-valued fields, if searching for all movies that list a single language, regardless of what other languages are listed, we can use the syntax that we've employed here. If we'd like to filter for movies that use both Korean and, say, English, we can do that using the $all operator. When applied, this filter will limit results to those movies that list both Korean and English among their languages, as we see here. The all operator filters for documents with an array as the value for the key specified that contain all of the elements listed as the value for the all operator itself. So the semantics of this are, find me all documents where for the languages key there is an array containing all of the elements listed here in this array. These elements can occur in any position or order in the array field, but they must each be present. The PyMongo driver supports the entire MongoDB query language, so we can do exactly this same thing in Python. Here's an example. Note that here we're specifying a filter with this dictionary, and then passing this dictionary to the find method. And this should actually be find called on the movies scratch collection, because that's the collection we've been looking at here in Compass. And if we run this, we see that the results are now limited to only those movies using the languages we've specified. Movies that also use other languages will be included, but every movie returned uses both Korean and English. The semantics of the languages listed in this dataset are such that the languages are listed in decreasing order based on the frequency with which they are used in each movie. If we want to do an exact match on movies that use Korean and English, with Korean being the language more heavily used, we can do an exact match on the array containing these two elements. Korean first, followed by English. Note that we're not using the $all operator here. What this filter means is, find me all documents where for the languages key, the value is precisely this array. Korean listed first as the 0th element, and English listed second as the element at index 1. Applying this filter in Compass, we can see that there are 27 matching documents, and that in fact for each of them, the value for languages is an array with Korean as the element at index 0 and English as the element at index 1. If we flip this and look instead for movies where English is listed first and Korean second for the languages field, we find 23 documents. For these types of queries, MongoDB is looking for an exact match against the key in question for the array we've specified as the value in the filter. With respect to array fields, one last thing you might be interested in doing is filtering for documents that have a specific value in a particular slot within an array. For example, we might like to filter for all documents that list Korean as the primary language for the film, regardless of what other languages are listed. We can do that specifying the array index we want to match against using dot notation. In Compass, this looks like this. As we scroll through the results, we see that every movie lists Korean first. We can do the same thing in Python, though we'll need to wrap the key for our filter in quotes so that it's a valid dictionary. Now, it's a little hard to read this to find just the languages field, so let's limit the results to just provide the languages field. We can do that using a projection and pass that to the find method. As with most MongoDB query language syntax, we define a projection as a document. The semantics of this projection are that only the languages field for any matching document should be returned, together with the title to provide a little context. Find will accept a dictionary as its second argument and interprets this as a projection specification. In projections, we want to use 1 for all fields to explicitly include, and 0 for any fields you want to explicitly exclude. If we only explicitly include fields, as we've done here, MongoDB assumes we want to exclude all others. Running this, we see now that our search results are much more readable. However, I wasn't being precise when I said that project would return only the languages and title fields. The underscore ID field is special because it is the unique identifier for all documents in a collection. To eliminate the underscore ID field from a projection, we must explicitly exclude it. Let's do this and then run again. There. Now we have just the title and languages field for each result document. In addition to making results much more human readable, projecting fields means that the other fields are not even returned from the server. Each document here represents an entire document matched by our filter, but because of the projection we've specified, the server will only return the title and languages fields rather than all of the data for each matching document. So we can use projection to significantly reduce the amount of data that gets transmitted between our client and the database server. That's a pretty good overview of how to filter on array fields in MongoDB and a brief introduction to projections. We'll do a lot more work with both topics in this course in other lessons.
From this course title, you might get an impression that you will be building a bunch of code and you actually be building an app. Well, that is almost true. In reality, we are going to provide you with an app, a backbone app, and you will be tasked along the way to see how it works, to understand how it operates, and to manipulate the data that it generates and reacts with. You will also be tasked along the way to do some things slightly off Mflix to either improve it or to just change a little bit of the application behavior. But more of that ahead of us. For now, we are just going to be looking into how this application actually works and which dependencies we have. The application that we're going to build is called Mflix. Now, any resemblance with a popular media streaming service is pure coincidence. This application in concrete, our Mflix, will have a few considerations and functionality. First, we'll have some sort of user management where we can create users and log in users and so on. We will have a video catalog where we can scroll and see some interesting information about popular videos that are available on the platform, with a list of details of the movies based on several different rankings or some other sets of different filters that we can create, and obviously the actual detail of the movies. So once you log in and have your account created, if you look for videos, the application will allow you to look for them and find them. And obviously, you can also look into the details and have some sort of user interaction with this particular application. Okay, so this is how the application is supposed to work. We are also going to see internally in terms of code how it is actually being composed and which are the components that make for the application. The application itself, it's built so that it can run on your local laptop and using Atlas to store all the data. For that, the version that you will be downloading from the lecture notes and from the handout material will have some slight code gaps somewhere that we will ask you to download and improve or complete the functionality. But more of that a little bit further down the road. For now, what I will ask you guys to do is pretty much just have a folder path that you will be using for this course. In my case, I'm going to be using users MongoDB Coursera. And in it, I'm going to have a folder and I'm going to call first app or building app, whatever you choose. It's okay. Once I am inside my first app, my working data set for my Mflix application, and after downloading to my local laptop the handout material, I will unzip inside this folder, my working folder, that same code. This is running code that you should be able to run in your local machine. I also recommend you to, on this working folder, create a notebooks folder. Now, this is where I'm going to be storing the handouts that we're going to be providing to make sure you can follow through with the lectures that we are going to be teaching in this course. So this is where I'm going to put all my Jupyter notebooks. Not needed for now, but will be needed later. Once I have the folder for notebooks and unzipped my mflix application, this should be the directory structure that I have in my working folder. As in any application, a README file is always convenient to have, and this is no exception. This here will tell you the dependencies that you need to install for running our application, and some other instructions like the run.sh file that will allow you to run the application. It will be our executable. Now, make sure that you have all the dependencies installed. As you figured out by now, we are going to be using Python, the best, most beautiful language in the world, Flask, which is a very popular web framework for Python, PyMongo, obviously. We need to talk to MongoDB, and PyMongo is the way to do so. And some other libraries like Faker and Flask, Login, and Bcrypt. All nice libraries to work and to use for our needs. Now, before we go and run our init run file, you can see here that it will launch an application, a Flask application. There's a couple of things that we need to edit beforehand. The first file that we need to be editing would be our db.py, this file here that will control all access to the database. Now, the first thing that we need to edit on this file will be the Mongo client connection string. As you can see here, I already done my due diligence and added up my own personal mflix cluster on Atlas. You should do the same thing and put your connection string here. Once you've added it to your db.py file, you are ready to run your run.sh or run.exe. Once we have it up and running, you will see that we're going to have a up and running server on 127.0.0.1 and on port 5000. Great. And as you can see, this will be the exact same location that I'm going to be connecting to show you mflix up and running. Sweet. But let's understand what's going on under the hood. Now, the mflix app itself, it's composed by a couple of different interesting modules. The first one is our mflix.py. This is where we are going to actually instantiate all the Flask application library and consequent libraries that we need to run the application. Then we have another Python module called db.py. Now, db.py is responsible for the connections between the application and the database. Think about it as our model layer, if you're coming from an MVC kind of standpoint. Therefore, the db.py talks to MongoDB, in our case, in Atlas. This is where we're going to store all of our information. And mflix.py instantiates and uses the db.py methods to forward all the requests. There are other things like the templates that we'll be using to prettify and show you the correct HTML, well formatted with all the information that we need, that you can have access and scroll around within the templates folder. There's also obviously static information like the CSS that we are using, or even the source data file, movies.json, that you previously imported in other lectures. Another important one, or not really that important, but just a important functionality of our application, is that we allow you to log in and log out, and that's controlled by the auth.py file. Give it a look to understand how we are dealing with the authentication. So, to sum it up, our mflix application is a runnable application. You need to configure the connection string to Atlas and put it up and running with run.sh that will instantiate the Flask application called db.py to request and submit any information to MongoDB on Atlas. Once you have that, the only thing that you need to do, go to your local browser and browse away the magnificent interface that we built just for this course.
In this lesson, I want to talk about how mflix queries MongoDB to generate its homepage. By examining how the mflix page is generated, we'll actually get to learn about the following cursor methods: sort, skip, and limit. So let's take a closer look at this page. I want to point out a few interesting characteristics. First, you'll notice that there are 46,000 movies in mflix, but this homepage is only displaying the first 20. Moreover, you'll notice that the 20 that we're displaying are all very well-known films here in the US. And the last thing I want to point out is if we go ahead and scroll down and click Next Page, you'll see that the next page displays the next 20 movies, movies 21 through 40. So let's go ahead and look at the code of inflix to see a little bit of how this works. So let's go ahead and take a look at inflix.py, and this is where our function exists to generate the homepage. And this is the function, and we know this is the right function because of app.route being for slash. So whenever we go to the root part of the website, the homepage, this is the method that will get called. And the first 25 lines or so here are just about making sure that we understand what page we're on, seeing if a certain genre was selected, or seeing if a query was made about a text search. But we're going to ignore all of that for the most part. Really all we care about here is this call to get movies. And this is where we actually make the call to the database. And as you can see here, we pass in 3 parameters, pass in our filters as we set them up, we pass in the page that we're currently on, and we pass how many movies we want on each page. And that's going to return to us a list of movies as well as the total number of all of the movies in the collection. So let's go ahead and look at get movies. This is in db.py, and here you can see the get movies function. And let's go ahead and copy this and put it in our Jupyter notebook so we can actually play around with this function a little bit. So the first thing I'm going to do here is define the parameters that we go ahead and pass in to get movies. So this is a very simple example. We're not making a text search or searching by genre. So our filter is just going to be an empty dictionary. And we want this query to be for the home page. So we're going to say page is equal to 0. And just like on the home page, we're going to render 20 movies per page. Now I've gone ahead and simplified the get movies function a little bit by removing the function and kind of splitting up the code across multiple cells so that we can more easily see what's happening. And in this first cell, this is where we ensure that the home page is filled with movies familiar to our users. So by default, when we query MongoDB, the documents are returned without any particular order. But to make sure that these movies are relevant to our users, here we're going to sort them by the number of reviews that they have. Now obviously there are many different ways that we could implement this, but this naive approach works pretty well for this example application. And as you can see, our sort key uses dot notation. And that's because we're sorting on a value that is nested through a series of nested documents. And this is the exact same dot notation that we use when we're filtering for embedded documents. In this case, we're now using it for sorting. So very simply, we just pass in our filters to find, and then we append the sort method, passing our sort key. And then, of course, similar to how we do sorting and aggregation, we also have to pass a direction. So we want to sort things so that the most reviews are at the front. So we're going to sort this descending. And then the second thing we want to do is go ahead and get the total movie count. So this query is going to currently return all of the movies. And so when we run count, you can see that indeed it does return all of them. And so the first thing this query does is go ahead and counts how many documents are on this cursor. And we go ahead and store that in this variable called total num movies. And this is one of the return values of the get movies function. Now, it wouldn't be very cool to send all 46,000 movies to our user. They certainly don't have time to look at all of them, but moreover, it would take a long time to send them over the network and to render them on the page. And that's why we limit the number of movies that we're sending. We're limiting our results to 20 per page. When users aren't on the home page, we're going to need to go ahead and skip over the entries that precede the pages that they're currently on. And that's what skip will let us achieve. In this case, since page is 0, movies per page is still 20, this is going to evaluate to 0, so we're not going to be skipping any for the home page. And when we go ahead and turn this cursor into a list and look at its length, you can see that we're getting 20 movies. And if we look at the first movie, if we look at tomatoes and look at viewer and look at the number of reviews, you can see that there are quite a few reviews, and that's why Titanic is the first movie that we see on Inflix. Now we can go ahead and simulate going to the next page by setting page equal to 1, and then running the same query again. We have no filters, we're sorting on the number of reviews, and then this time we're skipping, hopefully, 20 movies. And as you can see, we are now returning 20 less movies than what would have been returned if we returned all of the movies. Let's recap what we discussed in this lesson. We looked at these 3 common cursor methods, But moreover, we saw how together they can be used to generate our movie homepage, as well as through the use of skip and limit support pagination.
Throughout the code of Mflix, we can find some queries being submitted to the database. We have queries on movies where we express some filters. We have other queries directly matching a particular field like _object_ID, or even some other searching by its email address. Now, some of these find operations that we've seen are very straightforward. We are filtering based on one single value for one single field, which is great. However, MongoDB offers much more extensive sets of query operators that allows us to find documents using multiple operators. And that's the purpose of this lesson today, querying movies using some of these query operators that allows us to do a bunch of different things around our documents. Let's see some of this in action. Within the course handouts, you will see this Movies Query Operators Jupyter Notebook. Let's go ahead and load it and just do the typical steps. Let's import our needed modules, our PyMongo and our pipprint. Let's make sure we can connect to our Atlas cluster. Again, it's the same cluster being using with the same username and password. Don't forget about that. And don't forget where to get it. Go to your cluster, press the connect, look into your connect, your application, and copy the URI. Once you get it, paste it, and replace the password placeholder. Now let's go ahead and run this, and we have a connection. No errors, all good. Now, since I was born in 1983, yes, I am that old, I would like to know all movies launched after 1983. So that means every single movie where the year of launch is greater than equals 1983. And that's exactly what $GTE stands for, greater than equals 1983. Once I run this, I can see that the first preprint is the count, 32,584. A lot of different movies launched since I was born, and I can guarantee you I did not see all of these, which is fine. In the first few years of my existence, I was quite a young child. I wouldn't be watching a lot of movies like this. Now let's say that I would like to, reduce the scope of this amount of data for the ones that correspond to the period of my childhood. Let's say from 1989 to 1999. And here we can use the operators greater than equals again for the year, but also combine it with $LTE. LTE stands for lower than. In this case, since I want to go from 1989 to 1999, I can also go to lower than 2000, being exclusive the year 2000 onwards. If I run this, I can have a smaller amount of information, or a smaller amount of movies launched in this period. But let's say that I'm also only interested on a specific set of different movies, or in this particular case, a different set of years in which movies were launched. I'm only interested right now in knowing which movies were launched in 1995 and 2005 or 2015. For that, I can use the $in operator over the field year to find exactly that information. This will filter out only the movies which were launched on all of these 3 years combined. Once I run the query, I can see that 3,980 movies were launched in those 3 years. A very prolific set of years. But we can do further than that. I'm going to keep the same initial predicate of saying that I want all movies which were released in 1995, 2005, and 2015, and also exclude the genre adult movies to cope with some audience restrictions. All right, if I do that, and I can combine any sort of different fields with different query operators, I can have a very expressive query language that allows me to do a lot of different combinations to find my result set. MongoDB has many more types of operators, from comparison to logical to elements, and also some specific like geospatial or text operators. The query engine allows us to be very expressive in the types of queries we might want to execute in MongoDB. Please find in the lesson notes the links to access the full extent of all query operators currently available in MongoDB. As a quick recap, the query language is very expressive, and we have several types of operators to be used in our queries. We can express the queries that apply several different operators in a single field or even in multiple fields in a single query. And we are only bound by our imagination. I can assure you, you will not be bored trying different operators every day. That's all we got for you on query operators.
In this lesson, we're going to discuss the match operator. And specifically, we're going to discuss a common pitfall that you might be subject to when you're querying for subdocuments that are embedded in an array field. And we're going to talk about specifically how we can use the match operator to eliminate this common pitfall that people fall into. Unfortunately, the Influx app doesn't need to query for documents by subdocuments that are embedded in an array field. So instead, we're going to walk through kind of a contrived example because this topic, match, is actually really important. So let's go ahead and take a look at a random document in our movies collection. And here I'm making sure that it actually has a comments field. And I'm just going to go ahead and project out the comments. And just so that we're all on the same page, as you can see, comments is an array field. And each element in this comments array is actually an embedded document. And this is the kind of schema where you'll encounter this specific pitfall. Let's go ahead and go down to cell 5. Now we know from previous lessons that we can query for this document here using dot notation. Here I'm saying I want to find a single document where a comment was made by Samuel Tarley. And awesome. We can go ahead and see here that here is our document, and there are 3 comments, and one of them is from Samuel Tarley. But let's look at another example. Let's say that I wanted to actually find this document not only by one field, but actually by 2 fields. If we look at our past result, you can see that this comment by Samuel was actually made in 1988. So let's say I was having a query where I not only wanted to find this document by the commenter's name, but also when this specific commenter made the comment. In this case, I want to make sure that it is less than or earlier than January 1st, 1995. And when we run this query, we get the same document. We have the same 3 comments from the same 3 commenters. This is the exact same document as our last query. So we know that we can actually query for documents based on multiple fields when they're embedded in an array. But there's actually a pitfall in our logic here. We're actually returning this document not purely based on this criteria. If this was not a find one, we would actually return more documents than what we'd expect. So let's go ahead and look at this. If we scroll down to cell 7, here you can see that I'm running the same exact filters projection, but now I'm going to skip over this document that we've been looking at. And I'm just going to get one document, so we're just getting the next document that MongoDB will find. And as you can see here, we do have a comment from Samuel, so it seems like it's good. But if we look at the date, you'll notice that the comment was made in 2000, which is not less than January 1st, 1995. And the pitfall here is that what this query is actually saying is it's not saying, let's find comments from Sam that were also made before 1995. What we're actually saying is, let's find documents where one of the comments is from Sam and also one of the comments is from before 1995. We're not specifically saying that Sam's comments have to be before 1995, but that's probably what the person who wrote this query was actually looking for. And this is the common pitfall. And the way that we get around that is by using the match operator. And here's the syntax. Here we say $LMatch. Of course, we say first the field that we're querying on. And then we're saying, for this field, what do we want our documents to look like? Well, we want our embedded documents, we want to match them based on having this name and being before this date. And now, when we run this query, we're limiting to 2. So we would expect to find the first document that we've been finding every time. And then we'd expect to not see this incorrect second document. We'd expect to see a document where Sam, so this is our first one, Sam, before 1995, all good. And if you look at our second document, we also have a comment from Sam before 1995. So let's recap what we discussed in this lesson. So we saw that when we're querying for multiple fields in subdocuments that are embedded in arrays, sometimes our logic might not be what we think it is, and we might actually return more documents than we're expecting. And to get around this issue, to actually query for multiple fields on the same embedded document that's in an array, we're going to need to use the LMatch operator.
MongoDB allows you to define rich data types, multidimensional data structures that are very similar to object-oriented programming language objects. That means that we can define complex objects like arrays with subdocuments embedded, or even fields with just subdocuments, which in turn can have complex data structures with them. In this particular lesson, we are going to be looking into how to query on a field of our movies collection called Tomatoes, which corresponds to Rotten Tomatoes viewers' reviews, and how to use the magic of the dot notation to explore and express really complex queries within MongoDB. Okay, so we have these documents with subdocuments in them, but what's so special and what's so great about them? Most relational systems can also define columns of data type XML or even blob, where we can just throw into it very complex data structures. The reasoning behind MongoDB is the ability to actually query within those data structures without just having a dump of that data in a particular column in a relational world. Therefore, you can model your data in such a way that it doesn't restrict the queryability of your application. Now let's see how to use this in action using our mflex application. In this Jupyter notebook that you have access through the handouts of this lesson, you will have a way of expressing those same queries against our mflex database. Now, first step would be to just import the necessary modules. In this case, I'm going to use pymongo and pprint. Second step would be to express our connection string and the way to connect using pymongo mongo client. Now, don't forget to get this particular URI. You can just go to your Atlas cluster, go to connect, say that you want to connect from your application, and basically copy the URI in place and replace the placeholder for your password by the password of our user, that in our case is analytics-password. I've done that due diligence myself, and I can just pure and simply connect. No errors, everything seems to be good. Now, to get started in analyzing exactly how the substructures of our documents work, let's have a look to the Titanic movie. Now, I know there's some duplicates here, and we'll take care of this later. So therefore, I'm going to just find one where the title is Titanic. As we can see here, we have very, very complex data structures and lots of embedded fields and arrays and all sorts of different data types here that we might want to treat in a particular fashion, or even just query on those fields as we would query on normal, let's say, single field root level fields. But what's interesting about this is that we can isolate it a little bit in Python. So let's look into tomatoes. Now, again, tomatoes is basically a field that condenses the information of Rotten Tomatoes for this particular movie. And as we can see here, we have a very, very rich internal data structure. So tomatoes itself is an embedded field that has other embedded fields in it, which we can use to express queries. Those embedded fields themselves, some of them are from ints to date times to strings and so forth. So we can use this data structure to do some very interesting queries. Going a little bit deeper, I can see that tomatoes.viewer has a couple of other embedded fields themselves: meter, number of reviews, and rating. Now, if I would like to get all the movies that have the same rating as this particular Titanic movie, I can just use the Titanic Tomatoes Viewer rating field, put its value into a variable that I'm going to call rating, which in this case is 3.6, and use that value here to express a different query. Now I'm going to look into all different movies that have the field Tomatoes Viewer Rating, again, a subfield inside of another subfield, with the same value from previous movie. And I'm going to print only the title, so it doesn't mess up with my view screen here. Let's pause just for a second and look into this dot notation. What is this anyway? MongoDB uses the dot notation to access elements of a complex object arrays or subdocuments or embed documents that are embedded within the documents of a collection. For example, here in movies, we have that for accessing a field within tomatoes and within viewer, we will need to use this dot connecting those different fields. If we look back into the structure of this particular document, we see that we have several different data types, or fields in this case, that could use the same dot notation for us to access the embed information within it. Tomatoes is one of the most complex ones, but you could have writers which has an array, and we can access the elements or indexes of those arrays to express queries as well. You're always using the dot notation. So every time we want or need to access fields within subdocuments or within arrays, we will be using the dot notation. Now, the dot notation is not only used for the find query or for the filter that we express in our queries. It can also be used for our sorts, meaning that we can sort on any embedded field that we wish. In this particular case, we are going to be using tomatoes.lastUpdate. We are going to be sorting the results by the ascending last update. Once we do that, we can see that we have our title, Rampage, that has been last updated on 2012. Then the following is the suspect in 2014, and so forth. This capability shows us that no matter how deep our field is, if we need to express a query or even a sort condition for our queryability or for our application, MongoDB allows us to do that using the dot notation explicitly to get the type of queryability that our application demands. And this is how you can express queries using embedded fields. A movie streaming service that does not let their users make comments on the movies they like, it's probably not a very good one, and there's a lot of improvement room for their user experience. Netflix is nothing like that, and it does allow you to provide feedback for feature analysis and for us to do something more interesting with the service later on. Obviously, Netflix will be storing that information in MongoDB. And for that, we have a particular method I would like to talk to you guys today about, which is this insert1 method here that allows us to insert a document into MongoDB collection, in particular to our comments collection. Now, this is probably the simplest command that we can find in MongoDB, but I would still like to tell you all about it. So let's see this in action. And for that, I'm going to use, again, our Jupyter notebooks. There's one called insert1 for this lesson. And let's do the typical imports of importing everything that we need to use this particular notebook. We start by pymongo, piprint, and then we're also going to import bison object ID and the built-in datetime support of Python, which is datetime. Now, as usual, we need to provide our MongoDB Atlas URI so we can connect to our instance. And it will be a nice idea for me to just print it out to see if we actually get a correct connection in place. So let's do just that. Once we run this, you can see that the connection to the database is well executed. So we can move along. Now, for inserting a single document, we are just going to insert, in this particular example, a dictionary. I'm going to create here a dictionary that I'm going to call comment with some data on it. The data that we are storing in MongoDB is name, email, movie ID, text, and date. All of them of different data types. Name and email are the typical string data types. Movie ID will be a bison ID, which I'm going to generate one right here. It's going to be a fake comment, so that's all good. Text, again, string, and then date. I will be using datetime UTC now. Another object that I'm going to create here is this bypass validation flag that I'm going to put to false. Now, the last thing that I need to do is call my mflix comments insert1 method, passing along my fake comment and this flag. Now, why is this flag here and what is its purpose? MongoDB allows us to define on a collection basis a validation of our documents. Obviously, if we don't have one or if we just simply want to bypass it, MongoDB currently supports that in a very easy manner. We just need to pass a flag saying if we want to bypass the validation or not. For this particular example, I am going to do that just to show you that we can. So if I do that, I get back a insert1 result that I'm storing in this variable here, insert result. Insert result has two different fields. As one field called acknowledged, which will tell me if the command that I just emitted was acknowledged by the server. In this case, it's true. So we got there. We got to the server. Fantastic. And now it also can tell me if it's been acknowledged, what's the insert ID of our document, because we are not providing an _ID field. And as you know, if we do not provide such _ID field, MongoDB will create one for us. And there it is. But obviously, we can, in fact, provide an _ID if we wish to do so. Like, for example, here we are going to set our _ID field to a string with the value some _ID field. If we do so, we can see that it is true, it has been acknowledged, and the inserted ID is the name or the string that we provided inside of the document. All checks correctly. And lastly, we need to also realize that a primary key cannot allow any duplicates. So if we try to insert the same document again, or even just a different document with the same _ID field, an error will be raised. MongoDB makes sure that if you try to store two different documents with the same field value for _ID, a duplicate key error will be raised, as you can find it here. And this is all on insert1 method. Within our mflex application, users can post comments on movies. Now, different users or even the same user may post different comments on a particular given movie. So, for example, I can come over here and say, this movie is great, which it actually is, and it's pretty good. Awesome. So I can see here that my post has been correctly posted and submitted. In this lesson, we will look into the update mechanism that MongoDB offers so we can implement such a functionality like putting comments into movies. Not only we are going to be looking to adding comments to a particular existing movie, but also how to increment a counter within those movies documents. In method add comment to movie, we implement the feature that enables the user to add comments to a given movie. We collect the movie, and by updating an embedded array called comments, we implement this functionality. Now we are applying here what is a common MongoDB pattern called subset, where we keep a subset of the dataset, in this case corresponding to comments, within the movie's document. Using this subset paradigm, we will be storing the information of a given comment in two different places. You can find more information on why you would want to do this and learn about other schema design patterns in this lecture notes auxiliary content. Within this implementation, we are about to do two different things. First, we update comments field in the movies document, and then we add to a collection that contains all comments in the application the same comment as the one that is now currently added to that comments embedded array. In the movies collection, we are using the push operator to push a comment to the comments array field. Now, if we wouldn't be using an update operator, we would be replacing the document, sending back and forth the full amount of comments alongside with the full amount of the information that characterizes a movie back and forth. So this operation here allows us to save a lot of bandwidth by not sending the full amount and making our operations way much smarter and faster. And that's the main reason why we have these update operators. We are also keeping a movie comment cache limit, a set number of movies, a limit to the amount of movies we are keeping within our movie document. Now we do this for two main reasons. First and most important one is to avoid unbounded arrays. If we keep on growing comments without bound, therefore an unbounded array, we will certainly reach problems in terms of documents being too large or even completely uneven document sizes across our collection. The second is to optimize the reads from the movies collection. We don't need all the comments all at once. We just need to fetch the latest ones, and that's exactly what we are doing here by specifying not only the limit, but also how we sort them. That way, we only have a first view of the comments of a movie, but if we want to get them all, we just need to go back to our database, look for it on the comments, and get the full amount. Smart, right? With slice, sort, and each, which are MongoDB update operator modifiers, combined with the array operator, in this case push, it allows us to express conditions on how the update operator handles the field values. In this particular case, we are implementing a capped array by defining a specific set of a slice or a number, a limit for our slice. We are defining that our array of comments will be capped to that value. But we are not over with update operators here. We also keep the effective number of comments made on a movie by incrementing $inc operator, a field that keeps track of those same comments. After we're done with the update, the next step would be to just add the incoming comment to our comments collection by inserting one and passing along that same comment document. In terms of update operators, there are two kinds. We have array update operators, where we have add to set, push, pop, pull, pull all, and even $position operator. But we also have field update operators, where you can set, unset, inc, current date, min, max, mul, rename, and set on insert, and a bunch of other new operators that we'll certainly be adding on to this update functionality. The important thing to realize here is that the update operators enable us to make changes on existing documents in MongoDB without the need for application-side logic. For example, we don't need to keep track of the counter ourselves. We can just ask the database to increment. Or if we would need to get the min or the max value, or even multiply the value that exists in the document without even reading it, we could just do that by setting an update operator. So basically, we leave it to the server the functionality of updating certain conditions given the state of the document without actually needing to read it. To recap, we've used update operators to avoid replacing the full extent of documents on every single update. $inc allows us to keep incrementing the number of comments without even reading the actual number. It leaves it to the database to actually do that work. Push appends elements to the comments array field. Using the update operator modifiers, we can set a capped array to avoid unbounded arrays. And the usage of the subset pattern allows us to optimize the access patterns to comments.
All right, so let's dive into projections a little bit more. And for this, I'd like to use the aggregation framework. As is the case with much of the way that MongoDB works, particularly with respect to reading and writing data, nearly anything that you can do in the MongoDB query language, you can do in the aggregation framework. And with the aggregation framework, we have even more power in terms of projections, which are important for reshaping data, as we're going to want to do in cleaning up this movie's dataset. Now, for a number of examples here, what I'm going to do is just experiment a little bit to show you the ways in which we can use the aggregation framework for ETL work. And as part of these examples, we'll use the movies_scratch collection as the place where we create output to look at examples. Now, for this type of exploratory work, there's no reason to run against the entire collection. So what I'm going to do with all of these examples is limit the documents that I'm working on to the first 100 in the collection, using a $limit stage as the first stage in my pipeline. And as I mentioned, we'll always be dumping the results out to the movies_scratch collection. Again, doing this just to build up our pipeline that's going to reshape these documents. In considering reshaping, we're going to be looking at a stage we've not yet looked at, called $project. $project allows us to specify a projection on all documents that pass through this stage. So what we're going to do here is ignore the fact that we've already looked at splitting several of these fields into array-valued fields using an add fields stage. Where we're at this point is that we've done enough work on some fundamentals with respect to the aggregation pipeline, filtering, projecting, that we can then really begin to talk about how to use $project to do a lot of what we need to do with respect to cleaning up data. So the best way to think about a $project stage is as a tool for reshaping documents. As we saw in a prior example, I can stipulate that I want to include fields by simply specifying the field name and a 1. And I could explicitly exclude fields with the use of a 0. In this case, what we're going to do is pass through all fields of every document, but for some we're going to do a little bit of work to either clean them up or to reshape them in some way so that they meet our needs for the type of analysis and application building we want to do down the road. So any place in this project where you see a 1 simply means that field contains data that's good enough or that we're willing to work with. It's only those that have something else that you really need to focus on. There are a couple of silly fixes that we're making here as well. And by silly, I really mean just kind of tidying things up as opposed to fixing a real problem. This is one example. In the movie's initial dataset, there is a field called full plot. The only real problem with that field from my perspective is that it doesn't use camel case as the name of the field. So what I'm doing here is effectively renaming that field to full capital P plot. And as we saw with some other lessons, this is a field path specifier, and the semantics of this are find the value of the full plot key in all documents that pass through here. And what we're going to do here then is create a new key with this name and make as the value for that key for every document that passes through this stage the value of the same key with the slightly different name, full plot with no capital P. Here we're doing something similar in renaming the rating field to rated. I've found with this data set that people get confused about what rating versus rated. The rating field is actually the MPAA rating, PG, R, PG-13. And that with the name rating, people tend to get confused thinking that it's a critic's review or a viewer's review. But don't have that problem if we rename it rated. And then you'll notice here that what we're doing is that same split, only I've accidentally named it actors instead of cast. So fixing that, you'll note that we have that same split for each of these 6 fields here to convert each of the string values for these fields to arrays. But the cool thing about project is that because nowhere in here do we specify that the field director or writer or genre should be passed along out of this stage by specifying director:1, for example, we are not only splitting these string values into arrays, but we're also renaming these fields to their plural forms. So instead of director, we'll have directors, and instead of genre, we'll have genres, for example. So both a splitting and a renaming of the same kind that we did when we renamed these 2 fields. And lastly, what I'd like to point out is that we're actually going to create an embedded document here for IMDb. The movie's initial data set, if we take a look at this in Compass, currently has field values for IMDb rating, IMDb votes. In fact, there are 3 keys that all lead off with the name IMDb. So rather than do that in this data set, what I'd like to do instead is have a single IMDb key, and as its value, I want not a scalar value, not a string, and not an array, but instead an embedded document, or in Python parlance, a dictionary. And in this case, the dictionary then will have the keys ID, rating, and votes. And all we're going to do here is use the value for the IMDb rating key and the IMDb votes key, and simply use those values for these new fields that I'm creating in this embedded document here as the value for IMDb. This is not strictly necessary. I'm providing this merely as an example of some of the flexibility that the MongoDB document model provides to us in terms of how we structure data. The query language and the aggregation framework fully support this type of embedded document, and there are lots of reasons why you might want to do this in a data model. We're looking at one very simple reason here, and that is simply to save a little space. In other lessons, you'll get plenty of experience querying on these types of embedded document fields. Okay, so let's take a look at this as a whole. We're passing through every field that we find in movies documents. Some of them pass straight through, like title, year, released, and runtime. Others, we're splitting into arrays and renaming to their plural form. And others, we're doing some simple renaming. And finally, we're doing some reshaping here, creating an embedded document. So project allows us to define the shape of documents that are output from this stage using field values for documents that are input to a project stage. Now, if we run this, let's take a look at what we get as output. So again, we're sending the output here to the movies_scratch collection. And I also want to point out that we should only have 100 documents because we're limiting the documents that we look at from the very beginning. Okay, and if we go into our movies_scratch collection, note that there are just the 100 documents that we expect. And let's take a look at the shape of these documents. We're doing this as a test of whether our strategy worked as intended. So here we see title and year, runtime, released, being passed through as they were found in the movie's initial collection. Note that we have a directors, cast, writers, genres, languages, and countries array for each of those fields. But note also that we don't have that redundant director or writer or genre field that we had when we used the add fields stage in an earlier lesson. Lastly, we see that we have an embedded document here for IMDb with the expected values here. And of course, full plot and rated were renamed as expected. One thing I didn't mention is that we actually also renamed last updated, again introducing camel case. And you can see that if you look at the very last field in our project stage. Okay, so that's an initial example of using project to do some fairly simple reshaping of our documents, and I would say leaning toward extremely useful reshaping when it comes to splitting strings into arrays.
In this video, I wanted to talk about how when we make a comment in Inflix, like when I say what a great movie the Titanic was, when I submit this comment and the page reloads, I can go down and you'll notice that I'm also able to delete the comment that I created for myself. In this lesson, we're going to use this feature of Inflix to explain how you can delete data in MongoDB. Specifically, we're going to look at how to delete data in MongoDB using the delete one and delete many commands. So here we are in the comments list.html template file here in Sublime. And you'll notice right here, I'll select these lines of text, that this is what allows us to delete comments that are our own. So we check for each comment that we're rendering here, we check if the current user's email is equal to the comment's email. And if so, then we produce this additional HTML where we create a form that deletes this movie content. That's the action URL. And then there's, of course, a little delete button. So let's go ahead and go into Inflix to look at delete movie comment. And as you can see, this code is pretty straightforward. Pretty much the most of the heavy lifting is done by delete comment from movie. So let's go ahead and now look in that method in the db.py file. And as you can see, there's a lot going on here. And that's mostly to deal with the fact that we're caching the last 10 comments on our movies document. So I really wanted to just focus on just this first line of code, this use of delete one. And we're going to go ahead and look at our Python notebook to look at how this method works. In the code that we were just looking at, the comment was deleted by the comment's ID. But we can actually use any kind of filter that Find supports to also delete comments. So in this case here, I made a filter that says, what a great movie, which is the comment that I just made on Titanic. I'm going to store this inside the filter variable. And now I can go ahead and run this query and find this exact comment. And there you go. You can see that here's the comment I made, what a great movie, on, and this is the movie ID for Titanic. But we already know how to find documents. But I want to show that using the exact same filter, we can actually also delete comments. And so here's our delete result. And so now when we run this command, we would expect it to no longer return this document because it was just deleted. And that's exactly what we see. Moreover, if we go back to Inflix and refresh this page, we would expect this comment to go away. But it doesn't. Why doesn't this comment go away? And that's because this specific comment is actually stored on this movie's document. We cache the comments on the movie's document so that we don't have to make an additional call to the comments collection when they're just viewing this page. However, we can scroll down to the bottom here and actually look at all 405 comments and actually just make a single call to the comments collection. And in here, my comment doesn't exist. And that's because we actually deleted my comment, if you look back at the Python notebook, off of the comments collection. And that's how delete one works. But now what if we want to delete more than one document at a time? Well, that's exactly what the delete many method is for. Here, I create a variable that has the Titanic's object ID, and then I go ahead and put that into a filter. And so this should delete all comments in the comments collection for Titanic. So there should no longer be any Titanic's comments after I execute this cell. So now when I refresh this page, here we're looking at all comments. We would expect them to all go away. And they're all gone. I can no longer scroll on this page. There's no more comments. But you'll notice that it still says we have 405 comments. And that's because this number is actually stored on the movie's document. So let's go ahead and go back to this view of our 10 cached comments. And let's go ahead and remove these 10 cached comments. And let's also go ahead and update that number so that we don't see all 405 anymore. So here I can go ahead and do that. Here I go ahead and create a movies variable which accesses the movies database. And here I'm using the $set operator to turn comments into an empty array and reset our number of Inflix comments to 0 with the update 1 command. And now when I run this, it looks like it worked. But let's verify by going to Inflix. All of our comments are still here, but when we refresh the page, you can now see that there are no more comments, which is exactly what we would expect. So let's recap what we learned in this lesson. We learned that there are two methods for deleting documents in MongoDB. They both act very similar to find one and find, but they're called delete one and delete many. They accept a filter expression just like find would, but instead of returning documents, they actually end up deleting them.
Our Mflix application allows us to do a lot of different things, including listing, for example, the movies of our catalog. Now, this means that we perform a couple of queries to the database. For example, we have the query that allows us to click on a particular movie and go to its detail page, which is great. The query that allows us to do that is the get movie here that basically sets a query that looks for its underscore ID based on some underscore ID that we know, and we pass along and get back the movie details. Now that's all great and fine, but there's other functionality. Like, for example, if we want to find all the Titanic movies, we can search and it finds it for us. So all the movies that have the word Titanic somewhere either in the title, but also not that much, like Titan and Clash of Titans. Why is this related with Titanic? How does MongoDB know about that? To answer that and other questions, we can use indexes. In particular, in this lesson, we are going to look into indexes present in the movies collection. But before we go and jump directly into the different index types that MongoDB supports, it is important for you to realize that indexes are special data structures used by databases, including MongoDB, that allows us to do some enhanced functionality, like, for example, making our queries more efficient and faster. In MongoDB in particular, we have other functionality that's also supported by indexes, like, for example, the geospatial capabilities and the text indexes. Now, to help us out uncover the indexes in movies, we have, as part of this lesson and part of the material for this lesson, the indexes on movies Jupyter Notebook. Now, as usual, what we need to do is basically initialize by importing the necessary modules, connect to our Atlas accounts, and providing the URI. As you can see here, we are able to connect, no errors, and we have a database object. Fantastic. But what we are interested in knowing is what type of indexes do we have? Now, This method here, movies.indexesInformation, provides us back with a list of the existing indexes for this collection. In this example here, we have 4 underscore ID underscore, which is the primary key index of our collection. And then we have 3 other indexes. These are secondary indexes, indexes that the user, in our case, our application mflix, created to support its queries. So let's have a look into detail in a couple of them. Now, the nomenclature used by MongoDB to name the indexes is as follows. We're going to have the index field, then we're going to have an underscore ID and a value, either 1 or -1, telling us if the field itself is sorted ascending or descending. And if it's an index that spans over more than one field, like in this case, tomatoes.viewer.numReviews is a embedded field, and it's sorted descending, where the sign -1 will tell us just that. And then you have these keys that are exactly that translation. The key genres 1 and tomatoes viewer num reviews -1. All indexes in MongoDB follow that nomenclature, but you can set at creation time a different name. In this case, we've been lazy and let MongoDB do its magic. Now, something very interesting about MongoDB is regardless if it is a root level field like genres, or even a very nested embedded field like tomatoes.viewer.numReviews, we can create different types of indexes that span across those different fields, no matter where they are placed inside of the document. In this particular case, this is a compound index. Compound index stands for an index that spans across different fields inside your documents. So the combination of those two values on these fields will generate an index, a data structure that will map those two together. So we can fastly access all queries that inside on genres and the number of viewers on tomatoes. Now, although indexes are very cool, and they are used to enhance our reads and making sure that we have the combinations needed to, for example, do efficient sorts, it is important to raise to your attention that the fact that we have indexes, or the more indexes we have, the slower our writes on the collection that supports those indexes will become. There's also a max number of indexes, which is 64 per collection in MongoDB, so be careful about the number of indexes because they will have a penalty. Now, one of the things that we can do in MongoDB is actually explain how a query is executed. Now, to do this in Python, there's a completely different command using the MongoDB shell, but we're using our IPython notebook here, or our Jupyter notebook here. We can perform the explain by running a command on the mflix database. The explain command will be set by defining where we want to find, or what the command on which collection we want to perform, in this case a find on movies, and what's the filter that we want to actually execute. For example, tomatoes.viewer_num_reviews greater than 10. It's a nice query to do. And also we can define the type of verbosity of this explain command. Once we run this, we can see the execution of this query. There's different stages by which the execution of the query needed to go through, if the stage is an index scan or not, if it has a fetch stage, and a bunch of other information that is really, really important for us to understand if the actual execution has been optimum or close to that. Now, I'm not going to go into too much deep in terms of the weeds of the query engine and all the stages it performs, but you should be aware of the fact that every single query that is executed in MongoDB and in other databases will go through different stages. You can have, for example, call scan, basically stands for a collection scan. This is the worst performance you can get because it will go into all different documents of your collection and try to match them against your query criteria. But there are others like fetch, sort, index scan, shard merge, bunch of different stages that make part of your query. You will find some of them on your explain output. But getting back to the explain itself of our query, which is a filter on tomatoes viewer num reviews greater than 10, we can see here this field called winning plan. It takes an input stage, is a direction forward, and has a couple of other things which are interesting. For example, the fact that it is passing through an index scan in terms of stage. Another important thing here to raise up is the fact that it's using an index, and the index that's been used for this query is this tomatoes.viewer.numReviews -1. So it's using a single index to perform this particular query and return results in a very, very efficient manner. But getting back to our list of indexes, there is a particular index that I want to raise your attention to. This one here, title text, cast text, director's text. Now this means that this index here is a FTS, full text search text. Now, text search indexes are slightly different from, for example, single field indexes like tomatoes.viewer.numReviews, or even compound indexes, which are on genres and tomato viewer numReviews. The main difference is that text indexes do not just follow the exact match of a value against the indexed structure. They will take in consideration relevance. How relevant is a key compared to the different entries that are present in that index. In this particular example, the title, cast, and directors are all fields which are going to be indexed based on their text. That means that we'll be creating an index for text search support. So if we go down here to the notebook and execute this particular query here, where our filter specifies that we're looking for a title Titanic, we can see that we only find the exact match of the movies where the title is Titanic. And if we would change something like the title from capital K's to lowercase on the title, we might not find absolutely nothing because there will not be an exact match for that particular title in our movies, which is fine. That's expected. But we can also do another different type of search. We can specify that we are going to be looking to the text search, and we're going to be searching for the term Titanic. Once we execute that query, we can see that we can find several different movies, not just one. And not all of them match Titanic, either case insensitive, but also, for example, the fact that we have Titan on it. Now, why is that? Text search will take in consideration relevance. And that means that we're going to be looking to things like stemming of the term, case insensitive, diacritics, and even stop words. There's a bunch of different other options that I can specify in our search terms that will make this query result smaller or larger, depending on the type of fidelity that we want based on the term that we are providing for the search. We're not going to go into too much detail on that, but this is a baseline functionality that MongoDB supports based on a specific set of text indexes that we can specify on a collection. The limitation here is that you can only specify one text search index per collection in MongoDB. All right, cool. I saw some of the different indexes that MongoDB in this particular movies collection has. How can I create one my own if I want to? Let's say, for example, that we have this countries here field that I would like to start searching on or matching exactly or even sorting the results based on the countries that the movie is related with. Now, I could simply define a create index method passing along an array of tuples. Those tuples will contain the field key that I want, in this case, countries. In what sort of order do I want my index to be sorted? If I would like to have a text field, I could also specify that here, or even if it would be a 2D sphere or 2D index, that will be the type of index that I'm going to be creating. In this case, I'm going to create a top level, root level field, single field index sorted ascending. Once I run the command, it tells me back what's the name it was created with, following the nomenclature, the field, and the sorting order. As a recap on this lesson's topics, MongoDB has several different types of indexes. Now, indexes are used to optimize our query performance and the query access patterns that we use in our application. A collection may have several different types of indexes on different fields. Use them wisely, because the more indexes we have, the slower our writes will become. If we are optimizing our read capabilities, we might be putting some penalty in our write ability. That's all I have for you on indexes in movies lesson.
In this lesson, we're going to discuss the power of MongoDB's geospatial query engine. Specifically, we're going to look at how we can find geospatial documents within a circle on the Earth. We're also going to look at how we can find geospatial documents near a point, And finally, we're going to look at how to use 2D sphere indexes and how they kind of relate to geospatial queries. There are times that we have data that contains geospatial information. In the case of Influx, we have a special dataset called theaters, which is a dataset of different theater locations. We can go ahead and look at one example theater document, which looks just like this. As you can see, we have two fields, one being the theater ID, the second being location, which is an embedded document, where we have address, which is a human-readable version of the address, and then geo, which is a geospatial point. It's handy to structure a location this way because the address is easily human-readable, whereas the geospatial query can be queried by MongoDB in some very useful ways. If we further drill in to the geo-embedded document, you can see that it is formatted in this specific way, where we say type point, coordinates, and then an array of coordinates. This is actually a part of a geospatial standard called GeoJSON. When we use GeoJSON to define a location like this, we can then query for this document using some really powerful query operators. Here's a list of all of the different geospatial query operators. In this lesson, we're going to talk about two of the most common, GeoWithin and NearSphere. Let's go ahead and jump into Compass so we can easily see these geospatial points. If we go ahead and click the Schema tab, we can click Analyze, and then after a bit of analyzation, we can then scroll down to Location and open it up, and you'll see since we formatted our point as a GeoJSON point, we had this really nice little map of all the points on a map. Now here's the best part. We can actually zoom in here, and by holding Shift and clicking and dragging, we can actually select a subset of our points. This is an excellent way to visualize and play with geodata stored in MongoDB. And the best part is we automatically create a query up here in the filter bar. And as you can see, this query uses the special GeoWithin query operator. And as you can probably infer, this query returns all of the points within the circle. But let's go ahead and break down this query a little bit further. Of course, we're going to say which field we're talking about, which in this case is location.geo because we're using dot notation to query on an embedded field. From here, we can go ahead and use the GeoWithin operator. And now, since we're talking about locations on a map, we're really talking about points on a sphere, which is why we use the center sphere operator. And now this operator takes two parameters passed in via an array, the first being the center of our circle, where longitude comes before latitude. And now I want to point this out. This is longitude and this is latitude. This is backwards of how coordinates are typically specified. And this is a part of the GeoJSON standard and is the case for some very interesting legacy reasons that I'm not going to get into in this lesson. And then after we specify the center of our circle, the second parameter is the radius of that circle. And that is measured in radians. So most people aren't super familiar with radians. They're more likely used to something like miles or kilometers. So here we're going to use the radius of the Earth in miles and kilometers in order to convert between the two. So here we'll go ahead and take our example radius and paste it in. And then we can just take that radius and multiply it by the radius of the Earth in miles. And now we can go ahead and print that. And as you can see, it's 430 miles. And when we go look back our query, that's a pretty reasonable estimation. Now, GeoWithin supports other operators besides center sphere. I'm not going to demo these since they function the same as center sphere, but there's also box, polygon, center sphere, as well as the good old-fashioned geometry operator. If you want to learn more about these operators and how they function, I suggest you look at this documentation page, which will be linked to in the notes. The other operator I want to talk about is NearSphere. And now this is very similar to GeoWithin and CenterSphere, but queries executed with this operator will be returned in order by the distance from the center of our sphere, thus the near keyword. And so this is what the syntax looks like for NearSphere. It's pretty similar to GeoWithin, but now we're going to use the $geometry operator to define the center of our circle. And we also pass in a min distance and max distance determining the area of our circle. We don't actually need a min distance since we just want a circle, but you could put in a non-zero value here if you wanted to build a donut-like shape. Now it's important to point out here that min distance and max distance are both specified in meters, not in radians, like with center sphere. So let's go ahead and store this query, and then go ahead and execute it. Oh no, what happened here? Well, if we scroll down, we can see that it says unable to find index for $geoNear query. And that's because $NearSphere requires a special index on our GeoJSON field. But fortunately for us, it's very easy for us to create this index using Compass. We'll go ahead and go over to Indexes, click Create Index. I'm going to name it GeoIndex. We're going to select the field, which in our case is location.geo. We're going to say it's a special 2D sphere index and click Create. And just like that, we now have the special 2D sphere index. So now when we go back to our query, we can go ahead and try and run it again. And this time, we see documents. And now these documents are returned by how far they are away. And so you can see we have 1,000 meters, so 1 kilometer from this location, which is actually MongoDB's headquarters. You can see that there are 2 theaters within a 1 kilometer radius. This theater is closer, and this theater is a little bit farther away. Let's recap what we learned in this lesson. We saw how we can find documents that have GeoJSON coordinates within a circle on the Earth using the center sphere operator. We also learned how to find documents that are near a point using near sphere. And finally, we spent some time discussing which queries require a 2D sphere index and how to build one in Compass. In this lesson, we're going to talk about how we can graph data with MongoDB. Throughout this course, we spent time discussing the power of MongoDB's flexible data model and its expressive query language. This lesson is going to be focused on how to use MongoDB with a tool commonly used by data scientists and analysts, Matplotlib. Specifically, we're going to look at how to use Matplotlib to create scatter plots, 3D plots, and box, also commonly referred to as box and whisker plots, using Matplotlib with MongoDB. Before we get started talking about how to create each of these plots, we first need to talk about how we pass data to Matplotlib. When graphing with Matplotlib, it almost always expects the data to be passed in via one or more arrays. So for this example, here I've created an array with values 1 through 5, and then I take each of those values and using list comprehensions here, I square each value. And we can go ahead and print this to see what it looks like. And as you expect, we see 1, 2, 3, 4, 5, and 1, 4, 9, 16, 25. Now to pass these arrays to Matplotlib, it's pretty easy if we want to create a scatter plot. This is a common convention to go ahead and clear the figure. We then go ahead and set up our subplots so we can actually access our axes. And then with that axe, we're able to use the scatter method, passing in our 2 arrays. And then finally, we go ahead and show the plot. And when I scroll down here, you can see Matplotlib figures out these ranges of values on both axes and plots our coordinates. And as you can see, it forms a nice little x squared curve. And we can do this exact same thing for data stored in MongoDB. We go ahead and import PyMongo, create our cluster string, connect to our cluster, and then we can go ahead and write a query. Now in this example, I want to plot the length of a movie, its runtime, against its rating. So let's create a query where we return only documents that have both of these values. And then I'm going to go ahead and just project out just those 2 fields. We'll go ahead and create these variables, and then run the query and turn it into a list. And when we print this, as you can see, when we print just the first value, you can see that we get both our Metacritic and runtime values. However, like I demonstrated earlier, Matplotlib expects a separate array for each value, not a single array of pairs of values. To do this, we're just going to iterate over each value in our RM array, pulling out the runtime. And as you can see, this is now just an array of runtimes. And similarly, we're going to do the same thing for the ratings. So now that we have 2 arrays, each for one of the values that we're comparing, we can now go ahead and just pass this to Matplotlib. You can see that I'm using some additional parameters now. I'm using an alpha so that each point on the plot isn't fully opaque. So this way we can kind of see where lots of points overlap. And then also I'm giving a title and labeling my axes. And when we plot this, as you can see here, there is a bit of correlation. Movies that are very long in runtime seem to do pretty well on ratings. There are very few points where we have very long movies that have low ratings, which is kind of an interesting correlation. But I don't want to spend too much time analyzing this. I want to kind of show you more of the functionalities that you can do with Matplotlib. The same process can be applied to 3D plots, where we want to compare 3 values. In this case, we're going to continue to plot the same variables as before, but we're also going to see if there's a correlation between year and either of these variables. So first, we're going to go ahead and import the Axis 3D module. Go ahead and create our queries. This time, I'm making sure that not only does year exist, but also that it's an integer. And then, of course, I'm going to project out those 3 values. Going to go ahead and execute my query, turning it into a list of values. And just like before, we're going to use list comprehensions to pull out each variable. And very similarly before, the syntax is a little bit different now because we're creating a 3D plot. But as you can see, we're really just doing the same things. We're clearing our figure, getting our x, using the scatterplot function, and then setting our labels. The key difference here being that we had to use add subplot and passing in a 3D projection parameter. And when we go ahead and plot this, as you can see, we now have a cool little 3D plot. And what we're really seeing here is that there aren't very many years of data. We have movies that go all the way down to 1940, but as you can see, we don't really have any runtime data or any rating data for these values. Finally, let's talk about one more plot, which is the box plot, also commonly referred to as the box and whisker plot, because you have this little box and these lines that come off that kind of look like cat whiskers. Box plots are used to visualize the minimum, maximum, median, and first and third quartiles for a given set of values. In our case, we're going to plot several of these box plots representing each day in a week. Specifically, we're going to visualize the distribution of the hours of days that people watch movies on Inflix across each day of the week. To do this, we're going to use this watching pings dataset. So imagine for a moment that if every 15 seconds that someone is watching a movie on Inflix, we recorded that. And that's what each of these documents kind of looks like. It's a reference to which video they were watching, the user ID of the person, so who was watching, and then a timestamp for when they were watching. And so since we send this every 15 seconds that someone is watching a movie, we can now use this data to visualize a distribution of what hour of the day people are watching movies. But first, we're going to need to transform our data a little bit. So here we're going to use the aggregation framework. We're first going to take a sample of 50,000 documents. We're going to add some fields so that we know which day of the week and which hour of the day they were watching. And then finally, we're going to group by day of the week, pushing each document into an array field called pings. And finally, we're going to sort by ID, which is the day of the week, so that Sunday is first and Saturday is last. So what this means is that this cursor is going to return 7 documents. Each document is going to have an array field called pings that is going to contain a sample of the pings for that day of the week. But what we really want is an array of arrays, not an array of dictionaries of array of dictionaries. So let's go ahead and run this query, and then we can fix our data a little bit by pulling out our array of pings. And now that we have an array of documents, we want to get to an array of arrays. So now we can just pull out the hour of the day for each pings. And now we have that matrix. We now have an array where each entry is another array containing the hour of day for each ping. So the outer array is the day of the week, and the inner array is the hour of the day. We can now take this matrix and very simply pass it to the box plot function. And as you can see, we now have 7 box plots, each representing a day of the week. And the data kind of makes sense. There's more people watching movies on the weekends on average, but people are still watching a lot of movies during the week. And as you can see, people watch movies later in the day on the weekends. There's lots of people watching movies late at night. These little circles are outliers in our data, and we don't really see any of these during the week. And moreover, people seem to be watching movies later in the day on average relative to during the week. So to recap, we saw how we can create each of these different kinds of plots using matplotlib in MongoDB. It's very easy to get the information we want out of MongoDB. It just requires a little bit of transformation in order to make it work well with matplotlib to get the plots that we want.